Hello, everyone. Welcome back to Ask a Scientist Gaming, where we combine mediocre gameplay with expert science. I'm Ken Hansen, Associate Professor in the Department of Chemistry and Biochemistry at Florida State University. I'm a photochemist slash photophysicist. I shine light on molecules and materials and try to find out what happens to that light energy and track those various different processes, whether it's making and breaking bonds, moving electrons, moving protons, moving energy. But more importantly, joining me today is Dr. Ted Kolberg. Ted, if you wouldn't mind introducing yourself.
Yeah, thanks. I'm Ted. I'm in the physics department here at Florida State University. I'm an associate professor, and my main subject of research is high energy physics. So that means looking at the matter and the fields that make up matter on sort of the smallest imaginable scales, the most fundamental particles. And I'm an experimentalist, which means that what I mostly do is I try to build machines and detectors that enable us to answer like the interesting physics questions in that area. And I think we'll be able to get into a little more of what that involves as we play the games.
So what do you typically teach?
Lately, I've been teaching what's called intermediate and advanced labs. So these are for physics majors. It's usually maybe 10, 15, 20 students per semester. And we reproduce pivotal experiments in modern physics. So things like measuring Planck's constant using X-ray diffraction, the photoelectric effect, black body radiation, sort of the things that people would have been doing in a physics lab around like 1910 or 1920, which now are feasible for students to do using sort of modern equipment in the lab. So that's a fun class also because I get to meet all of our physics majors, which is a really interesting and diverse group of people here at FSU. We have some really strong students, and so I really enjoy that aspect of my job.
Man, that's pretty awesome. You go from the cutting edge Nobel Prize winning experiment to undergrad lab with a lab report. That's amazing. All right, equally important, what game are we starting with?
So I thought we would start with this game, Balatro. It is a sort of, I think it's a card game about playing like a solitaire version of poker as you're trapped in hell, from what I can tell. But it will make sense as we start playing it, so maybe I can just start a run here. So this is sort of a roguelite card game, so you do runs, and as you go through the run, you'll see that you sort of customize your deck according to whatever sort of strategy you're trying to execute. And the reason that the game is named Balatro, this Latin for joker, and you'll see that eventually I'll acquire these jokers across the top of the screen, which will in some cases radically alter how the game plays. But so far, we just don't have any of those jokers, and it looks like I can draw to a flush here. I have 3 discards and 4 chances to play hands to make this number of points. So I'm going to discard these and hope that I draw at least 1 diamond.
So I hadn't played this game at all, and I did a Google search, and one of the first pop-ups was on Reddit. It was, if I haven't played poker, am I going to be okay at this game? And the answer is apparently yes. I guess poker helps because you know the rules, but it's not really poker.
I guess you'll recognize the hands,
Yeah.
Although even there, depending on how your run develops, you might end up in a situation where like a high card could beat a flush in terms of points. It all depends on how the rules change. So, for example, this card is going to gain chips every time I discard a diamond, so that would give me an incentive to do that. And this banana will increase the multiplier of my score, but at the cost that it may be destroyed at the end of the round. I think this is a really good, strong card for pretty much any build, so I'm going to take that, and then I'm going to open one of these booster packs and hope to get a second joker that can help me out.
Schmodite, welcome back to the stream. First comment is, honest Pete, why am I the only one who doesn't know about this Balatro silliness? Balatro, is that how you pronounce it?
I think so. Everyone I've heard say it out loud says it slightly differently. Balatro, I guess.
Look it up on the internet.
Let's check this out.
Schmonite, welcome back. Hopefully you learn as we play.
This is a game that was made by one guy, which is a little bit remarkable. As you can tell, it doesn't necessarily have the highest production values, though I think it's quite clever in its own way. And it's written in this programming language called Lua, which I think is also really unusual for a game. So now I failed to hit my flush draw, so let's change gears here and maybe can play 2 pair here. That will be an okay hand.
So is the goal like top score or clear the deck, or what's the...
So what will happen is that as we go through the small blind, the big blind, and then the boss of each round, this score that's required to clear level sort of grows exponentially. So at the beginning, there's not too much pressure, but pretty soon we'll run into a situation where we're really scrapping to have enough resources to score enough points to clear the level. And that's where you want to kind of have a build in mind of what kind of deck you're going for, because if you're just playing all these random hands, then you won't improve any one aspect of your deck enough to pass those later rounds. Well, I don't know that any of this is really helpful to me, so let's go ahead. And then the boss of each level puts some additional constraint on you. In this case, he's going to reduce my hand size, which is annoying, but I hope survivable.
So is there a 2-player version of this, or is this single player?
I don't think there's any multiplayer version. There are mods for this game, but I haven't really explored those too much. I'm still struggling to beat the base game and all of its challenges. All right.
Cuddle puppy. Scientists got to get us kids into gambling before our self-preservation instincts kick in. That's the goal.
I am not a particularly big gambling fan. I think I know too much about math for gambling to be very fun for me. But I do like sort of playing cards and card-themed games, so this scratches that itch. But like, I don't know, if you ever play like poker in a casino or something, it's generally pretty tedious, I find. I mean, especially if you're playing Texas Hold'em and you're trying to win, not just have fun. It involves just like a tremendous amount of folding and only really playing hands in very specific situations. I used to play online poker when I was a college student, and there you could have like 5 windows open at the same time to keep yourself occupied, but it's not really an option when you're
man, that was peak when Texas Hold'em was just on top of the world online.
Yeah, well, I guess it was never exactly legal, but it was
legal enough.
tolerated, I suppose.
Yeah, until I guess people found out certain websites were scamming people, and Wild West.
Yeah, you used to have to like wire money to an account in the Cayman Islands to have it put into your account. Now I guess you could just use cryptocurrency. That didn't exist either when I was in college.
Yeah, that's amazing. So how did you learn about this game? Is this from students or just...
What did I learn about this game?
I'm always curious because we don't have the playground conversations anymore, right? We don't have commercials. It's kind of hard to keep up.
I think I heard about this game from the AV Club, like the Onions, reviews site. I think they named this like their game of 2024 or one of their games of 2024.
That's fun.
So as I'm playing here, I'm kind of like, I just unlocked this thing that increases my hand size, and I'm trying to figure out like what my deck wants to be. Right now, I've got kind of a bunch of mismatched things that aren't really converging on anything, but we'll see. Usually the first 2 or 3 antes, I'm on ante 3, ante 8. If you beat that, you won the game. So it doesn't usually start getting hard really until ante 4 or so. But I'm a little worried that I'm not converging on anything good. We'll see here. And
is everyone, as far as you know, is every one of these winnable? As in, like, if you play solitaire, there are some unwinnable combinations.
That's an excellent question. There are like seeded runs, so you can play a challenge with a given random seed, which is guaranteed to be winnable, but I don't believe every seed is necessarily winnable. And there's so many decisions that you make along the way, it seems like it would be hard to prove whether it was winnable or not.
Cuddle puppy. I believe the online gaming was banned due to lobbying by the horse racing lobby. Seriously, that sounds like it's true. Who goes to horse races anymore, honestly?
I used to live in France, and they would like pretty much every little town has a bar with this green like PMU sign over it, which means that they have the horse racing live, and you can bet on it like live from the bar. It's like everywhere, or at least was 10-15 years ago. And they have like this variant of horse racing where the guys are riding little chariots behind the horse. It always struck me as very strange looking.
That's the Ocho right there. That's spectacular.
Yeah, exactly.
Chariot racing. It's like Gladiator. I guess Ben-Hur is the more appropriate one. That one's for Jessica Clark. Hopefully she's watching. All right, Ted, we start every stream with one question. What got you to where you are today? I know you answered this. In fact, this is Ted's second time on the stream. It's been over 3 years. What did we decide?
I think it was February of 2022 the last time I was on.
Yes, you are the 28th guest, and surprise everyone, tonight is officially the 100th stream of Ask a Scientist Gaming, at least the 100th guest we've had on the stream. So cheers, Ted. Thank you for joining me.
Cheers.
What's funny is Ted joined me. I think I emailed him about a week ago about this. So I was supposed to actually be gone today. I was supposed to be in Washington, D.C. for an NSF panel. But yeah, they officially canceled all travels on federal dollars, basically. So I didn't go to D.C. Instead, I had a virtual panel today, which went till 6:30, actually. Ugh. It was a grind. It's
almost worse than having to fly to Washington.
Yeah, like Washington, at least, travel and hotel room and... But I'm glad we were able to do a stream tonight. And Ted, thank you for joining me again. Welcome back. He only came back for NARC, let's be honest. That's why he's here.
Last time I had this pretense, like I would practice a little bit on NARC and like learn how to play it. I mean, I don't want to kill any sacred cows here. It's not exactly the most fun game.
It's not.
So my plan to like become a secret NARC wizard kind of fell through, and this time I didn't even. Didn't even pretend.
Did I have the tutorial out last time? I don't know if I did. I've done a YouTube tutorial on how to beat NARC fast.
I should check that out.
Yeah,
that would actually be kind of interesting now that I'm a little bit familiar with it. I guess I'll be even more familiar with it by the end.
It would take like, I don't know, 4 or 5 solid days of gaming to be a top 5 player based on that tutorial. It's like, here's exactly how you beat the levels.
Okay.
Cuddle Puppy has some advice. Dr. Kolberg seems like he'd get all the flush boosting planet cards. He should get all the flush boosting planet cards. He's going for a flush every time.
Yeah. Oh. So I would like to find this. There's a card called Telescope, which guarantees that these planet boosters will always contain my flush card. So that would be great. You earn interest on the money that you don't spend after every round, so I'm kind of trying to build up a nest egg here before I start really just like ripping open every booster pack at the store. But now that I'm sort of above this like $50 mark or so, I guess that it'd be nice if I had some. There's also some cards which help you earn money faster, but basically the more money you have, the more options you have. We'll see what happens.
Fair. All right, so Ted, what got you here today? What were the forks in the road? What were the decisions in retrospect were major life-changing events despite feeling trivial at the time? How did you end up playing video games and talking science, particularly high-energy particle physics? So we'll start at 6-year-old Ted, if that's a reasonable starting point.
Yeah, I mean, I was always interested in particle physics as long as I can remember. I think I saw a Nova show when I was a little kid about the hunt for the top quark, which would have been going on at Fermilab at the time. And one of the things that got me really interested later on was the summer before I started high school, my high school sent everybody a reading list of suggested books to read that summer before high school, so we would like have something we could talk about when we got to school in the fall. And one of those books was this book called The God Particle by Leon Letterman, who was a former, maybe even current at the time, but he's dead now, but he was writing about the search for the Higgs boson, which at that point was still kind of in the future. And it's like a funny book. He has a lot of funny stories in the book and kind of tells jokes and stuff. But it was perfect for somebody of that age, and it really captured my imagination. And yeah, and when I went to college, I always knew I was going to major in physics, and pretty sure I wanted to do particle physics. And that's what I did. Mission accomplished, I guess.
Yeah, you knew early on. You at least knew early on you wanted to do particle physics. What led you to the academic route versus national lab, or I don't know what the industry equivalent would be?
Yeah, I'm not. There are lots of pathways from particle physics into industry. There was a point when I was a postdoc that I was thinking, if I'm not going to be on the academic track, as most people don't have the opportunity to stay on the academic track forever, thinking about what I might do instead. But I would have probably happily worked at a national lab if that's how the sort of, there aren't that many jobs in a given cycle. And some people might specifically target a national lab or specifically target a university, but a lot of people would just apply for whatever positions are open. I enjoy being at the university. I like teaching. And I think that university is a great place to work in this. And just before the stream started, we were chatting about, different things going on, sports teams and extracurriculars. There's a circus at FSU and all this kind of interesting stuff. And if you're at a national lab, which is much more kind of mission focused, you might have some of that stuff. But I'm pretty happy being at a university, and I don't know. Hopefully, my students are happy with me. Some of them probably aren't.
That's inevitable. But yeah, we are also talking about the circus tent is back up at FSU. Those of you not familiar, FSU has a circus. It's, I think, one of 2 universities that has a circus club. And so, yeah, we have a circus tent on campus. The story I've at least been recounted. I haven't looked into the accuracy of it, but basically the post-World War II, when it went from a women's college to an integrated college, there's a big donation from some circus entrepreneur that said, I want a club that's mixed gendered, and here you go, here's your money. And they have had an endowment, and they've maintained it, and the students run the club. They're the ones that are performers. They're the, announcers. I think they do the ticketing and management and all sorts of stuff. So yeah, it's kind of a fun side project for some students.
There's also this connection between FSU and the Ringling family or whatever, right? FSU now operates this Ringling museum complex
in
near Sarasota.
Yeah.
Have you been there?
I've been there.
Yeah, it's pretty interesting. They have replicas of I think they have some actual circus train cars from back when, I don't think the circus really travels as much anymore, but back during its heyday, they had this pretty all right, so this boss has this annoying feature that now that I've played a flush, I can only play flushes, which is okay because I want to play flushes, but I don't actually have a flush. I only have 1 more discard, so let's see if we can draw some more clubs here. So now I'm going to have to start burning actual hands that aren't going to score to try to dig to my flush. And I'm trying to think if there's a reason that I would prefer to go with these diamonds that I have 4 of, or these clubs that I have 4 of. And I think the answer is I want to go with the diamonds because I have a face card and this other card, which is going to multiply my score. So let's see if we can get lucky here. All right.
So yeah, here's a link to the Ringling Museum in Sarasota. It's kind of fun to see. It was interesting, to say the least.
I would recommend it if you're in the area.
It's got artwork. It's got some original circus, infrastructure. It also has this little model showing entire setup, which is pretty cool.
And since we're on the subject of circuses, I will take the opportunity to plug, for anyone who might be in the local Tallahassee area, we have the so-called Flying Circus of Physics coming up on Saturday from 11 to 4 on campus at the physics building, the Keene building. So you can come there. We're basically going to empty out our coffers of all of the demonstrations that we have, and we have some special demonstrations that we set up just for this, and there'll be a chance to meet and talk to a lot of the people from the department. Fun for all ages and completely free. So if you're around here, you might want to consider attending that.
There's a link to the open house if you guys want to check it out, because you bring in a bunch of departments. I got asked to do it, but I couldn't for kids' birthday reasons. But yeah, a lot of fun demos, a lot of fun, chemistry, we call them magic shows. Spoilers, it's not magic.
So I'm going to be working in something called the Alpha Beta Gamma Room, where we're going to have some things largely about radiation, particle physics, nuclear physics. So we have a cloud chamber where you can see particles coming either from cosmic rays or radon just in the air around us, or you can put a radioactive source in there and see all these particles blasting out.
Have you ever put a banana on it? Can you see it?
Probably you could, right? A banana's kind of a one of the more radioactive objects that we encounter in everyday life.
I was going to say, is that good for people or bad for people to know that? I don't know. It depends how you present it.
Yeah, I think eating the banana probably does more good for your health than the radiation that it contains is bad.
The thing about health response curves is pretty much anything has a little bit is good, too much is bad type scenario. I don't know if that's true for radioactive materials, but...
Well, I think there's some idea, right, that the optimal amount of radiation for life to evolve on a planet is probably not 0. Obviously, if it's too strong, then you can end up in the situation where nothing can survive long enough to adapt. But radiation also kind of powers evolution in the sense that a lot of the little copying errors, I mean, some of them are just errors that happen from the like biochemistry of your cells malfunctioning, but other things, it can be that literally a charged particle like comes in and knocks a base pair apart in your DNA or whatever, and that maybe that unlocks the potential for humans to evolve the ability to design aircraft carriers or whatever. So
eventually or individually, we don't.
I mean, there's probably more than one mutation responsible for that, but you get the idea.
I love that though. A million monkeys, one gets hit with a particle. All of a sudden it's Shakespeare.
Yeah, exactly.
I like it. No African swallows will be harmed in the flying circus of physics.
I don't, unless we've added some new demos since last time, I don't think so.
Are you going to vouch for that? Maximinus, welcome back. It's good to have you on stream. But yeah, if you guys have any questions for Ted Kolberg, he's an expert at high energy particle physics, in particular, work at the Large Hadron Collider and the CMS detector. So he is happy to talk about any topics related to those. Also cloud chambers and flying circuit. What else do you have? The cloud chamber plus what else is here?
Oh yeah, what else? We have a very cool demo that's like it's basically the concept of a nuclear reactor. So we have lots of spring-loaded little traps with ping pong balls inside. And then there's like little laser beams over the top of it. And when a ping pong ball breaks the laser beam, it causes the ping pong ball underneath that location to also get launched up. So you can see how from one interaction you can very rapidly create a chain reaction, and basically, you know, you drop one ball in and it will bounce around for a minute, and then within a few seconds they'll all be going. And that's kind of similar to how a nuclear chain reaction works in like a reactor or in a
you get to watch it go critical. This is a commercial thing, or this is something you guys built?
It's something that the department built. It looks like a bunch of custom stuff. You know, we have a very good machine shop, and we have a very good guy who works on our demos. So we have some cool stuff. You know, I think there's kind of a fraternity of these like demo guys at different universities. And my sense is that it's a point of pride for them if they have some, you know, some physics demonstrations are just completely bog standard that like everybody has them. But if you have something which is truly unique in your department, I think that's kind of a fun.
It's fun.
thing. So I'm likely going to lose now because I have just one hand left. I only have to score 4,000 points, but I don't quite see how I'm going to do that. I think the best thing I can make here is a 2-pair, queens and sevens. I don't think that's going to get the job done. I don't have a flush. So...
Man, sort by rank and suit is a really convenient function here. Like, that's...
The game would be borderline unplayable without it. There's a kind of a classic game design problem.
Oh, that was not bad, though.
All right. So hopefully now you get the idea.
Man, they should sell some of those demos on, like, Etsy, right? Start a company. There's enough people that would buy that demo, right?
I mean, there are demos that you can buy sort of pre-packaged, you know, these companies like Klinger or whatever that specialize in educational physics stuff. I think the problem is that there's not enough of an economy of scale to really make it very cost effective. Like, how many college physics classes are there in the country? There's a lot, but there's not tens of thousands, right? So I think the market for those things is always kind of small. And as a result, I mean, I deal with this class that I was talking about. You know, we have all these sort of instructional objects, some of which are quite dear. You know, we do a lab where we measure the charge to mass ratio of the electron, and that involves like a blown glass bulb that has like mercury vapor in it so that you can see the path of the electrons coming off of the cathode. And you know, they don't last forever. They can break, or if any room air leaks in, then the mercury kind of leaks out or gets diluted and it doesn't work so well anymore. And like, those things can cost, you know, many thousands of dollars to replace. So I think if you're able to build things in-house, it's actually quite advantageous.
Yeah, I looked into buying a cloud chamber at one point, and there's like two different, it's bimodal in what they sell. There's like a crappy version where it's like kind of assemble it yourself and it'll work okay, and then there's like the $1,000 version that is good, but also pretty expensive for a cloud chamber.
All right, so we're going to go on the straights plan now this time. So I got this card that lets me make a straights with a gap. And again, multiple such gaps. So really, I should be able to play an awful lot of straights here. So like 9, 8, 6, 5, 4 now is a straight.
Wow.
And then this guy will give me, every time I play a straight, this guy will gain plus 15 chips. So this is like, the ingredients for a successful run is like to have a card that makes your hand like easier to get somehow, and then something that scales, because you're, like I said, the points that you need to score every round is like growing exponentially. So if you're just like linearly adding to the power of your deck by adding like one card at a time, eventually you fall behind the arms race. But this guy, you know, if I fall behind to the point where one straight anymore isn't enough to win a round, then I'll have to play multiple straights each hand, and this card will get even more powerful then, because it will be gaining 15 chips, you know, more than once per time. So I think I can build a straight like this.
I want to believe, and I'm 100% certain there's an Excel spreadsheet somewhere that just does this, right? Like has done the predictive math.
So what I was going to say about this like game design problem is that a lot of games have, in principle, you could calculate, if you look up all of the multipliers and everything, you could calculate ahead of time if your hand will score. And some people, like high-level players that understand the math well, may actually do that. But the game doesn't tell you. And there are some probabilistic things in the game. Like, I don't think I've had any of them yet, but there are, for example, some cards which only trigger like 50% of the time or something like that.
Oh, interesting.
So that would make, even in principle, then you wouldn't be able to do it. So this is a pretty good card because it's going to increase how much interest I earn. So I'm going to pick this and then try to avoid spending any money for a little while and see if we can amass a nice nest egg here.
I mean, it's nice to be good and to figure out how a game works, but at some point, like when I was doing World of Warcraft, when it went that far, it's like the fun was lost. Right?
Yeah.
Like it was just, it became a spreadsheet rather than just playing a game.
Some people like that, right? I mean, there are some games that are really just about that, and if you can totally plan out everything, for some people that scratches an itch. I have to do so much planning in my real job that I tend to just want to like play games more for the vibes.
I just want to play Sorry. That's it.
Yeah.
Like, random draw. That's what I need in my life.
Exactly.
With that said, I saw they dropped the trailer for the Switch 2 today.
I saw that too.
It's June 4th. It's coming out.
Gonna be some new Mario Kart games.
Yeah, I saw that Mario Kart, apparently open world gameplay, which is kind of weird, like Grand Theft Auto Mario Kart style. I don't know.
Nintendo seems to have a pretty good batting average with their flagship franchises, so exactly. I wouldn't bet against them.
Yeah, I'm waiting for Mario Maker 3. That's going to be my trigger moment.
You played the previous
one and 2. I still play 2. That's my go-to game usually. Just like a really hard Mario level.
7, 6, 5, 4, 3, 2, ace. That's a straight.
Wow. That is the ugliest thing I've ever seen.
What? Right? 9. That's not going to get it done though.
I love that. So would the skill you get early dictates your gameplay throughout. That's kind of fun.
Yeah, I mean, I like these kind of these like roguelite games. There's a kind of a crowded space of games using this general concept of like doing runs, and each run is then like subtly different. So my instinct is always to keep like pairs, because like one plan that you might have is to make like full houses all the time, but actually if you're trying to go for straights, a pair is like worse than useless because it takes 2 cards and you're only going to play one of them in your straight. So it feels weird to be discarding 2 pair, but I think it's the right move here. So
you get like massive payouts for a Royal Flush, 4 of a kind.
Yeah, and yet you can even, at a certain point, you can start getting like 5 of a kind, right? Because it's a 5-card hand, and as you may have seen, you have the chance to like add cards to your deck. So you might end up with 15 kings in your deck by the end, right? If that's your plan.
That's amazing.
Take every opportunity to like duplicate and add kings.
There's the Wild West of cards right here. Oh, Cuddle Puppy, I missed your earlier question. Not really a question. Are high energy particles just particles that have school spirit? Any comment, Ted? Particle physicist, PhD, works at the Large Hadron Collider. How do you feel about
I love the wordplay. I think one of the interesting things about particle physics is that how few properties particles actually do have. Like, you know, you think about like a car or a chair or something, like for your purposes, you may mostly care about its carness, right? You ask your friend, do you have a car? Can you give me a ride? You probably don't care about the details of the car, but actually the car is an incredibly unique object, right? Even if it's a Toyota Corolla, it's still like yours is different, right? The wear is different. You may have added or subtracted parts over time. So like every car, even if it's like the quote unquote the same car, really has a lot of distinguishing features that would make it unique. And particles are not at all like that. In fact, they're kind of the opposite of that, in the sense that as far as we can tell, not just every important or pertinent detail about the particles is really the same, is that like literally they are only the quantum numbers that they have and nothing else. They have no other properties, and they can't be distinguished. I mean, in some sense, it's even interesting to speculate on the idea that like every electron, in a sense, could be the same electron, right? If you have an event at the beginning of the universe where a bunch of electrons are created, we now think the universe is going to expand forever, but let's just entertain the idea that it would all come together in a big crunch at the end, which people used to think that might be. And then it's possible that you could trace the world line of one single electron back and forth from the beginning to the end of the universe multiple times, and that the reason that they're all exactly the same is because they're actually, in some sense, all just one electron. The way that we would think about that in particle physics is in terms of fields, that like the electron is like an excitation, if you will, of a field that's everywhere, and it's that field that kind of carries the quantum number of electrons. So electrons don't have any opportunity to be anything else than have the quantum numbers that field has.
So this idea that all the electrons are the same electron, is that a conceptual framework or a mathematical one? Like, how do I think about that?
Like I said, I think what we know about cosmology now says that the matter will eventually all fly apart, and it will either just end up as this incredibly diffuse like gas of photons, and then everything that else will be sucked into black holes, and then the black holes themselves eventually evaporate. So I guess in the end, electrons will end up sort of causally disconnected from one another, so they can't really all be the same electron in the sense that we're talking about. But you could at least imagine a universe where it was the case that they did all interact with each other at some point. And in that case, like for electric charge to be conserved in all those interactions, you know, that would be one way to guarantee that. It's just the same electron moving back and forth in time, making up all the matter and antimatter that, for example, was existing at the time of the Big Bang. Now, the last time I was on the stream, we talked about how it's actually really like a puzzle why the symmetry between matter and antimatter is broken, because we actually think that the laws of physics should treat them. We used to think that the laws of physics should treat them exactly the same. Now we know that they are treated almost exactly the same, with some few but very important exceptions, and that's like a really weird idea, right? Like, why should there be this symmetry between matter and antimatter, which is only, it's like very close to perfect, but very subtly broken. That's like the kind of problem that gets a physicist's mind wondering about what's really going on.
How confident are we that there's not exactly the same amount of matter and antimatter?
It's a good question. I guess that there could be somewhere very, very far away that we can't really make contact with, which there might be somewhere in the universe an area which was dominated by matter instead of antimatter, but we're pretty sure that there isn't. And the reason why is that when matter and antimatter annihilate, so imagine an electron and anti-electron come into contact, the only thing that can really happen there is that they neutralize each other, and then they have to produce a pair of photons back to back that have the same energy as the initial electrons. That's what will happen to them if you let them come in contact with one another. And because electrons have a well-defined mass, that means that those photons have a well-defined energy. And so you would, if you'd
see them everywhere,
pointed a gamma ray telescope at the cosmos, you would see a very distinctive signal from any region where matter and antimatter were coming into contact. You would see this monochromatic line, and nobody has ever seen it. So it's at least within what we call the observable universe, it doesn't seem like there are areas which are really dominated by antimatter.
That's intriguing.
Maybe they're just really far away. Maybe someone's observing it right now for the first time, and we'll read about it tomorrow morning.
That's what's fun about physics. All of it could be broken with one observation.
That's just like a good old-fashioned straight.
So how's the gameplay going?
It's good. So I got this card, the Hiker, which is one of my favorites. Every time I play a card, it permanently gains 5 chips. So my deck is just kind of becoming stronger by me just playing the game. I strongly suspect that this card is a trap in the sense that the scaling probably isn't fast enough to actually win, because even though I love to pick this card, I seem to always lose when I do. But like I said, we're here for the vibes, not the map, right? Let's keep the map to the science discussion, and I'll just play Balatro in a somewhat suboptimal way. I also guess that this blank card does something if you unlock enough of them or something, but I only have $33. I'm not going to spend $10 on something that will have no immediate effect on the run.
Would you be happy or sad if somebody came in chat and just destroyed your gameplay, revealed all the secrets?
There are definitely people that are extremely good at. I think this game has become very popular streaming because it has that bewitching quality of being pretty easy to understand what's going on, but very difficult to master, and the strategies can get pretty deep. So if you find high level streamers playing the game, people do these over explained runs where they literally talk through every decision that they're making in the game, and some of these guys could talk about just the first ante for 2 hours or whatever, all of the strategy that goes into deciding which card you pick over which other card. I'm pretty sure I'm going to lose here. I have only one hand to make.
So Balatro has 1.5 thousand viewers right now on Twitch.
Okay.
Should we stream under that instead of science and technology? Let's do it.
People might be interested in it.
Yeah. Well, what I love is our title is Dr. Kolberg, High Energy Particle Physics.
They're going to read it and think that Dr. Kolberg is some kind of self-generated title to express my extreme competence with Balatro, but I guess they'll be disabused of that notion pretty fast when they actually start watching.
I was just say they're more likely to assume it's Dr. Disrespect for Dr. Pepper or whatever arbitrary doctor status.
Was Dr. Pepper, was there a real doctor involved in Dr. Pepper?
Let's see. For origin. I learned this was the second most popular soda drink in the US right now, actually, which I did not expect.
This is why I was always more of a Mr. Pibb fan. He sounds a lot less sort of ostentatious than Dr. Pepper.
Yeah. Who introduces themselves as doctor, honestly?
If you met someone at the grocery store, you wouldn't introduce yourself as Dr. Hansen, right? It'd be kind of
one thing I am conflicted about when I see a medical doctor and they're like, "Hi, I'm Dr. Blah blah blah." I'm tempted to I'm Dr. Hansen. It's a pleasure.
And they'll ask "What's your specialty?" Chemistry. Oh.
I hated that class. Is what their response would be.
I guess if you make it to be an actual MD, you must have had some level of interest in chemistry, right? Isn't that one of the main things you have to study?
Nurses and doctors, that was my least favorite class. I hated that class, and it's often a weed out class for a lot of medical professionals. So
my dentist took physics at FSU. He said it was his favorite class. He thought it was super fun and easy.
Did he remember the professor?
He didn't. But
it's like Dirac.
I mean, pretty soon I'll have been here long enough that I will remember. I will have overlapped with people that graduated even some time ago. But this guy being a little bit older than me, and me not having been here all that long at that time, I probably just didn't recognize the name. But a lot of students probably don't remember the names of their professors. I can remember the professors of my physics classes because I was super into physics.
Yeah.
Mostly I can remember. But if you ask me who taught my American history class or whatever as a freshman, I guess I also do remember that one now that you mentioned it. But
That one shaped you.
it's the exception that proves the rule, if you will.
All right. So Dr. Pepper was invented by Charles Alderton, a pharmacist in Morrison County Old Corner Drugstore in Waco, Texas, experimenting with different flavor combinations. The unique drink became known as Waco and eventually later changed to Dr. Pepper. Why did it change to Dr. Pepper?
Interesting.
Oh man, there's a Dr. Pepper museum.
So he's a pharmacist, so he probably wasn't an actual doctor. That almost makes it worse. He's like a pharmacist pretending to be a doctor.
This stream brought to you by Dr. Pepper.
Have you ever been approached by anyone wanting to sponsor the stream?
Oh, no, I have not. We don't have enough viewership for that, but I'd be curious. I should get sponsored by like Proof or something. Have somebody just donate beers to us.
They would probably do
Some
it.
local one, yeah.
That's interesting. Upgrade 4 of a kind by 3 levels. So every time let me show you what I'm talking about here. So each of your hands has a level. We didn't really mess with this too much in the last couple runs, but it might become important here. So this is like the number of chips in the multiplier that by default you will get for playing that hand. But they have a level, and so they can be leveled up with those planet cards that we were playing earlier. But then this is offering me the opportunity to upgrade 4 of a kind by 3 levels. And I have this thing called a double tag in my pocket, which will actually double this. So that means it will upgrade 4 of a kind by 6 levels, which will make it an extremely powerful hand. So I think we should try to get ambitious and see if we can make a deck.
But how many frequent 4 of a kinds do you get?
Not very many, but we can start working on the plan, right? So we should figure out like what card we can try to get a lot of. So there's some ways to duplicate cards. And there's ways that I can open booster packs to pick more cards. So just for the sake of the argument, let's see if we can dig to a 4 of a kind here.
I like it. All right, digging deeper. Morrison is credited with naming the drink Dr. Pepper. Unfortunately, the origin of the name is unclear. The Dr. Pepper Museum has collected over a dozen different stories how the drink became known as Dr. Pepper. So, the answer is unknown.
All right.
Fun factoid for everyone. We got on Dr. Pepper. Oh, yeah, Dr. Dre.
I kind of have a taste for a Dr. Pepper right now. I guess I'll stick with the beer, but
I have root beer, if that's close enough. But I do not have Dr. Pepper.
I didn't really like it as a kid until somebody recommended that you have a Dr. Pepper with a slice of sausage pizza. And for some reason, that combination unlocked something in my brain to like understand Dr. Pepper.
Who was the guest? I think it was Jake Linford. He did Dr. Pepper, so I did Dr. Pepper and rum. That's pretty good. That was like, rum and Coke, but with Dr. Pepper.
I think of Dr. Pepper as a mixer. It's kind of a bully of a flavor.
Yeah. Oh, it's heavy, but if you have enough rum in there, it balances it out.
Cover up. Start peeling the paint off the walls.
It's like an upper and downer. Let's do it.
It's like... I guess you can't buy like Everclear or Bacardi 151 in Florida, right?
It's what? Is that real? I didn't know that.
I think they can't sell booze over 100 proof in Florida. I could be wrong about that.
Oh.
But definitely in college, we would, it would be like, oh yeah, the most booze in the least volume. You got to get like Bacardi 151. You'd be like pouring it in somebody's dorm room and you'd like miss the cup and it would start taking the paint off of the desk or whatever. It's like, are we sure we should be drinking this?
It's cost effective though. Limit of not alcohol content. Proof. Let's do proof. I want to know blood alcohol levels. Keeps telling me blood alcohol levels. Awesome. Just give me a number. Florida law prohibits that a distilled spirit greater than 153 proof may not be sold or consumed in the state.
Oh, 153. So Bacardi 151 you could do, but maybe not Everclear. Everclear's 180 proof, I think.
153 is such a specific number. I mean, all numbers are specific numbers, but this one seems arbitrary. Unless they, like, Everclear lobby pushed.
Well, yeah, the existence of a product that has a heavily marketed proof of 151, and you have to wonder which came first.
Yeah. If that was their target, they're like, Florida's a big enough audience. We need to come in below this threshold.
I'm feeling that I can draw to a 9 here and score this, what will be a very emotionally satisfying 4 of a kind.
You might not win, but you will get 4 of a kind. Oh my god.
No.
Tension.
To settle for a lowly full house. So I picked this Fibonacci card, which is actually very strong. If your card is in the Fibonacci sequence, it gives you +8 multiplier. So probably I should be building towards that instead of this.
Wow, that's another
foolish,
fun sequence of number selection.
I always liked that. Like in my high school, we had what was called honors math, which was basically a way of like delaying all the kids that were already ready for like algebra, trigonometry for a year, so that more kids could catch up with them and have like a big enough class for a whole math class. But we did all kinds of interesting stuff in that class that we didn't do so much of otherwise in high school math. We did a lot of probability, which I always really enjoyed, and it's a big part of my job now, understanding like probability and statistical inference. And we also did a huge amount with things like the Fibonacci sequence, you know, how it like appears in nature and all these things, the number of kernels in each row of a sunflower and stuff all goes by the Fibonacci sequence, and it converges, the ratio, right, converges on this golden ratio, which is an important number in like architecture and art. It's like very pleasing to the eye to have things with a proportion of like 1.618 to 1, right? Like the aspect ratio of these monitors is probably close to that ratio.
And I'm curious, I've never actually looked into the accuracy of those claims of Fibonacci sequence matching. Is it inherent to the biology, or is it just sometimes it happens?
Yeah, it's a good question. I realize that I'm repeating that sort of factoid without really having a lot of actual knowledge.
Well, it's one of those things like, look how elegant this relation is, and then it's like, it kind of fits. But what are the error bars on that fit?
Right.
What's your R squared of the... But it's close, right? Because I mean, I teach group theory and symmetry, right? Like true symmetry is a rare thing, but kind of symmetry is very, very common, right? Biology loves that, but it's never. I mean, our heart has a hand in this, right? We're not perfectly symmetric.
Yeah, there are people, right, who have like. It's rare, I think, but there are people whose body is like a mirror reflection.
Yeah,
they have their
it's the wrong orientation or
their
wrong
organs on the other side of their body.
Yep.
So again, that's like a funny thing. That's like it's almost like protected by a rule, but then there are exceptions. Which again, in physics, that's like when you see something like that with the human body, you think, well, it's a very complex system. There's all these different levels of chemistry and genetics and biology and stuff interacting with one another. So maybe it's not surprising that you have like approximate conservation laws that are sometimes violated. But when you boil down to like elementary particles that really just have 4 or 5 numbers that completely defines their existence, the idea that relatively rich and complex like approximate symmetries can evolve from such a simple system is like really the kind of thing that gets one interested in something like particle physics.
Well, I like the biological equivalent, right? Because our DNA, our proteins, our amino acids all have the same handedness. There's no person that spontaneously has like left-handed when it should be right-handed. But every once in a while on a macroscopic level, the heart is the wrong direction. And that blows my mind, right? Because the fundamental units say it should be this handedness. And all of a sudden, now we'll just flip a heart around or flip a stomach around because nature's weird like that. Whew.
Yeah, I doubled the card that lets me increase my hand size by 3. So if I'm ever going to get 4 of a kind, I feel like it should be in this round.
I mean, you got to go for 4 aces, right? This is...
Well, especially because that would trigger this Fibonacci card.
Yeah, it's a moral imperative.
Trigger it, in fact, like 8+ times, because I also have this card for one more hand that re-triggers every card, so they will get played twice. But
speaking of moral imperative, R.I.P. Val Kilmer. I don't know if you've ever seen Real Genius, classic 1980s science nerd movie.
I have seen it. I don't think I saw it until relatively later in life. It's supposed to be about Caltech, right?
Yep. Well, it was filmed at Caltech. Did they define the university? I think they did, but it wasn't a real.
Oh, here we go.
Holy
we got
cow,
there, folks. We did it. Watch the points roll in.
GG's. We are in that one.
I scored so many points, they lit on fire. Look at that. 28,000.
You blew their minds.
All right. That was very emotionally satisfying.
What did you need to win that round?
I needed 7,500.
Blew it out of the water. Congratulations.
If you keep playing long enough, eventually, like, they can't even, it doesn't fit, like, the floating point number that you need to score doesn't fit, and they have to go to, like, scientific notation.
Oh, man. Does this game have a kill screen?
So once you win, you can go into endless mode, but unless your deck is very, very strong, indeed, you won't last long because that exponential growth really starts to bite.
And when did this game come out?
Last year, I think. There we go, 4 of a kind, and it's another Fibonacci. Things are happening to me now.
We're doing it, ladies and gentlemen. I mean, when things go right, they probably go right pretty aggressively.
Yeah, often you'll reach a point where the game becomes essentially unlosable, like your deck becomes so strong. I'm not at that point yet, but now that we have this Fibonacci thing to build towards, that's really going to help us. So like upgrading 7s to 8s is really good there because 7's not in the Fibonacci sequence, but 8 is.
So how many different types of upgrades does this have?
Oh, we can look. So I've unlocked 139 of 150 Jokers.
Wow.
And there's different decks that have different abilities.
Jeez.
So there's a lot of permutations of what can happen.
I was going to say, the combinations.
When you start, you only have, I don't know, maybe 40 of the Jokers or something like that.
So what's the end game is unlock everything and...
Yeah, I guess. That's what I like kind of about these, like, roguelike games, though. It's kind of like a game... almost like a board game, right? Like you learn the rules and then you can just kind of play whenever the mood strikes you. It's not like you ever finish the story or whatever.
Yeah.
And like, okay, and now that I know what happened to Mr. Balatro, I can like put the game back on my shelf.
Yeah. It's like you can win a game, but solitaire never ends, right? Yeah.
Yeah.
Anyway, we played. I'm excited to talk about the game, but we should talk about some particle physics. So it's been 3 years. What's the new development in your life, in your research, in the CMS detector?
Yeah. So last time I was here, we talked about the upgrade project that I'm doing. So I'll just briefly introduce that so people understand more what I'm talking about. So LHC collides protons together to produce new heavy particles, and we use protons. They're not really the ideal particle, actually, for our purposes. It would be nice if we could use a particle which was really truly a point particle, like an electron. The problem is that electrons are very light, and that means when you accelerate them in like a magnetic field, they radiate energy. And it turns out if you do this, like you would do this problem as like an intermediate physics student to show that the amount of energy that's radiated for a given amount of acceleration goes as like the 4th power of the mass, or 1 over the mass to the 4th power. So electrons being like 2,000 times lighter than protons, they radiate like millions of times more energy, or more than that, than protons in the same sort of setup. So in the same tunnel as the LHC, there actually used to be an electron accelerator in like the 80s and the 90s. But this was limited to a fairly low energy by the effect that we were just talking about, that they would lose so much energy just being... To move in a circle, you have to have an acceleration towards the center of the circle, and this would cause them to radiate like a huge fraction of their energy every turn around the machine. So you're like lighting up the whole French power grid to consume the energy just to keep them moving at the same speed, much less accelerate them.
Yeah.
So that puts a real sort of upper limit on what kind of accelerator is cost effective to build. Protons, they don't have that problem because they're heavy, they radiate relatively little, but they have another problem, which is that they're not point particles. We know that protons are actually a bag of quarks and gluons, and it's kind of like a atomic nucleus in that sense. Like, we know what the constituents are, and we know the forces that bind them together. I'm delaying them, by the way, because I'm going to lose on the next hand, so I can just finish my explanation.
You haven't lost if you don't play.
Exactly. There's another thing about playing poker at a casino. They don't really appreciate that style of play so much.
Yeah. No more free drinks for you, sir.
As a result, even though the protons have a huge amount of energy, the fraction of collision events in which they really give up all that energy in one single interaction between two of the constituent particles is very small. So that means we need to do a tremendous number of collisions in order to produce the particles that we're interested in. And actually, maybe this would be a time that we could do one of these predictions before I give the answer, which is how many collisions per second the LHC actually does.
All right, ladies and gentlemen, we're going to do a prediction. We're going to pop up a question right now that Ted wrote before he came on the stream. We'll give him some time to lose at the game. But the question for you guys is, and if you're not following, click the follow button. Your standard internet units, you can spend them on making us take a drink. You can request a factoid. You can unlock an emote, or you can just have pride in answering the questions correctly. The question for you guys right now is how many Large Hadron Collider collisions per second? So this is running at like maximum. I guess the range is big enough. It doesn't matter if it's running at maximum efficiency. The question is how many collisions per second when it's fully operational? 1 million or 1 billion per second? 1 million or 1 billion. So you have a error bar of 1,000 on this one. So it's either one of those two answers. But if you guys have a guess, put it in there right now. You can't Google, you can't chat GPT. What's your best guess on the number of collisions per second?
ChatGPT might also just make up an answer that sounds authoritative but bears no relation to reality. You gotta be careful of that.
I'm going to check what chat would say.
It's gotten better. If you're using like these O1 models or whatever, they're pretty smart about physics, it seems to me now.
Yeah. ChatGPT. I don't want that. This guy? All right, let's see what ChatGPT says. Yeah, if you guys have a guess, put it in chat right now.
Yeah, so that's part of the right answer, and when we reveal the answer, we can explain what it said and how that relates to the answer that we're looking for.
It's fun. We should run all our Ask a Scientist questions through ChatGPT. Just shoot students how poor it is at answering a lot of these questions. Any guesses how many collisions per second for the Large Hadron Collider? If you haven't done this before, click the predict button at the top of the chat. Use that to pick one of the two answers: 1 million or 1 billion. Nobody has confidence in this answer right now. So we'll see what the reveal is on this one. It is not... ChatGPT does not get it correct. All right, Ted, what is the answer? 1 million or 1 billion?
Yeah, so the answer is much more than a million, closer to a billion. It depends a little bit on some of the parameters of the machine, but a billion puts you in the right sort of order of magnitude. And so we do the collisions 40 million times per second, but each interaction has many proton-proton collisions in it. So the protons are not in a stream, they're in bunches. And it's more like you should picture a train with discrete cars coming through the experiment. So because of the need to use strong electric and magnetic fields to kind of shape and guide the particles through the ring, that all just works out better if they're in bunches. And so as we increase the luminosity of the machine, that basically means how much useful collisions we're producing per unit time. We do that by not putting more bunches in the machine, but by putting more protons in each bunch. So you imagine the train is already got as many cars as it can have, and now we're basically like packing more people into each train car. And so we've reached the point where there's like several dozen, close to 100 collisions per bunch crossing. And so you take this 40 million number, that's how many train cars per second, and then you multiply by 50 or 100, and that's what gets you into the realm of 1 billion collisions per second. And even the collisions which don't produce a Higgs boson or anything else interesting for us to study, what they still do is they put a tremendous amount of charged particles blasting through the detector every time that happens. So even if the collision wasn't so useful for like our data analysis, and in fact most of these collisions will never even be recorded by the experiment because there's no hard drive on Earth big enough to save all the data, we have to be pretty choosy about which of these things we actually we actually record. That process is called triggering. We could talk more about it later, but there's a tremendous amount of damage to the materials of the detector because of all these charged particles moving through. So you're basically sitting in a radiation field that's comparable to like the inside of a nuclear reactor or something like that. So anyone that's done anything having to do with like engineering materials to survive radiation knows that like radiation disrupts materials on their most fundamental level, right? It can not only break chemical bonds, but it can actually break up the nucleus of the materials and change one type of atom into another. So if you have a metal or a crystal or a semiconductor or anything like that, where you're relying on the kind of chemical purity of the thing, they don't last forever in that very harsh environment. So as a result, we have to periodically basically take out the sensitive elements of the detector and replace them. And we're gearing up for one of these replacement campaigns to happen in a few years from now. And so the project that I'm working on is to replace one particular part of the detector, a part called the NCAP calorimeter, with a new one, because the existing one will be so fried by radiation that you can't even get like the signals out of it anymore to make a reconstruction of what happened in the event.
So I was going to say, are these scheduled or are these just monitored and you can tell over time?
Oh, this has to be scheduled like decades in advance. So we're going to be doing just the process of opening up the experiment and stopping the accelerator and everything and doing these replacements will be a multi-year process.
Jeez.
And then the individual detectors that are installed during that time are each like a decade-long project of their own. And then you have to like organize to do that and convince the funding agencies to like pay for it and coordinate to do that. So that puts people were thinking of these upgrades even before the experiment actually started taking data. That's kind of the characteristic time scale of high energy physics nowadays, is that you have to be thinking always that far ahead in order to be ready for the next opportunity to replace things.
I mean, so presumably they quantitatively estimate this. If we have certain number of protons colliding, the gamma radiation will do X, Y, Z, and you have this time interval.
That's right. So there are calculations and models that will tell you what kind of impact you expect to have on your materials from all this irradiation. And of course, you can do experiments, right? You can build like one element of your detector and take it to a nuclear reactor and like put it in there for a while and then take it back out, wait for it to cool down until it's like safe enough to work with. And then you can measure like what happened. Now, it turns out that radiation damage is actually a subtle thing. Like the total amount of radiation that you receive matters, of course, but the mix of particles, which will be different, like in a reactor versus at the LHC, also matters, right? Wow. Alpha versus beta versus gamma versus neutrons, for example. Those ratios are not only different at a reactor versus the LHC, but actually, depending on where you sit in the detector, some of those forms of radiation are more effectively screened by like the earlier layers of the detector. And so the mix of radiation that you receive and the energy spectrum of the radiation you receive is also like time dependent and location dependent in the detector. So it's actually a super subtle and difficult problem to predict that accurately. And sometimes we have surprises in either direction. So you can have a case where things turn out to be more radiation hard than you predicted. Unfortunately, it usually seems to be the other way around. That the surprises somehow manage to come in the wrong direction, that things which you thought might be okay for longer turn out to need replacement sooner. And so there have been some kind of, I wouldn't use the term emergency because these are fairly slow moving things that take years to develop, but there have definitely been replacements that were not anticipated as part of the original run plan, which we've had to do on kind of a more of a like a rolling basis. But this big upgrade to what's called the high luminosity LHC. So the accelerator itself will also take this opportunity to upgrade itself to be able to deliver an even higher rate of collision. So instead of having several dozen protons in each bunch of the train, they'll have several hundred. So we'll have something like 150 or 200 collisions in each bunch crossing. Yeah. And then you think about how complex the resulting events are. So of those 150, maybe once in a while, one of them is interesting to you, but you have the other 149 also all laid on top. So it's like, imagine that you're trying to pick out a picture, and then somebody superimposes like 149 other pictures on top of it. And what you're trying to do is say, okay, who is this a picture of? It becomes extremely difficult. One of the capabilities that we can rely on to help make that process easier is to make the detector much more finely segmented in the spatial sense. So going from detector elements, which are like centimeters large, to like ones that are a fraction of a centimeter large. It's like kind of going from a standard definition television to a high definition TV. You can see much more detail in the same image. That's what we're doing with this detector. We're basically replacing a detector that had tens of thousands of channels with a detector that takes up the same physical space, but now has tens of millions of channels. And so our picture of these incredibly complex events is going to be much clearer than any experiment has had previously. So not only are we replacing the radiation damage stuff, we're replacing it with something which is inherently better able to cope with the amount of particles that we're going to have to disentangle. And this technology simply didn't exist at the time that the original experiment was being conceived, like in the 1990s in some cases, is when the original ideas were being sort of put in there. And now we have the chance to sort of do it with all of the innovations that have occurred in like electronics and in materials science of the last several decades. Now we're able to fold all that stuff in and make a really beautiful detector, which will have all kinds of capabilities that the original detector didn't have. So not only will we get more data, for each unit of data that we do get, we'll be able to extract more information from it. So it's kind of like a double whammy. We get more raw collisions, but we also have a better detector so that we're able to make sense of more and more of those collisions. And hopefully we will be afforded the opportunity to study some kind of new physics with this detector, which would be really fun, because that's sort of the reason why we're doing all this stuff. There's some things that we know are there. The Higgs boson we know is there, but it has many properties that are yet to be measured. So there will definitely be that aspect to the program. But there are also scenarios where we have been producing new physics all along. Dark matter particles would be one example of something that might already be present in the data, but our existing detector is simply not high fidelity enough, high resolution enough to see those signals and to like pick them out of the data. So that's the dream, is that this new detector type that has all of these additional channels and this huge spatial segmentation, it will have very fine time resolution down to like tens of picoseconds, so you can measure the arrival time of particles extremely precisely, which will tell you, for example, in this whole soup of particles which is coming out of these collisions, you know, those 150 collisions will be spread over a distance of like roughly 10 centimeters. And with picosecond timing, even if the collision products are traveling at the speed of light, you can actually reconstruct, like, did it come from like this region of space or this region of space? And the place where I'm putting my hands is like realistically like how far apart these distances are, right? So that's another thing that we'll be able to do, is like tell much more precisely, did the particle come from this specific interaction or this one over here? And that will eliminate a lot of sort of like combinatorial confusion that we have now of like which particles are belonging to which. You know, the Higgs, it can decay to 2 or 4 or even more particles before we detect it. And so it becomes a challenge to know, like, did I just coincidentally see 2 particles of the same species that are actually coming from 2 totally different interactions that have no correlation with one another? Or are they both coming from the decay of the same Higgs boson? That makes a huge difference, and we'll be able to tell the answer to that question much more precisely.
So what do they do with the old detector? Are you going to be able to take home a little slab, or are they going to put it in a museum?
That would be awesome. Unfortunately, the detector, by the time that it has received so much radiation, it will be sort of a radiological disaster. So I think a lot of these things will just be sort of entombed. Our experiment is already like 100 meters underground, specifically so the like farmers on the surface don't get irradiated. There's other like sort of civil engineering reasons to do it that way too, but that makes sense. People over time have tried to find ways to make former particle physics experiments like visitable things, like museums, and it is a really cool idea because they are really like astoundingly cool objects, and it would be great to give more people the chance to like see what they look like up close. But unfortunately, it's just very difficult to do that in a safe way because of all the radiation that they receive. Maybe after some years have passed, some of the components will be able to be a museum.
So I got to see the one of the PMTs from the Super Kamiokande experiment, which that one's not going to be as hot, obviously. That one's mostly photons, right? It's neutrino based, but yeah, it's just fun to see like the size of it. You don't appreciate how large some of these things are.
So there's another prediction on here, which maybe people will be more willing to guess on this one because the numbers are smaller, but connected to the same point that you were just making. I was curious if people had a guess what the diameter of the CMS detector was, and then maybe we could talk about why it would have the certain size that it does.
And the hard part about this is I'm curious how many people know what the CMS detector is. Do you want to give context before I say?
Yeah, so that's the experiment that I work on. There's 2 large general purpose detectors at the LHC. One is called CMS. That's the one which is much better than the other one, which is called Atlas. I will give the clue that Atlas is even much bigger than CMS. But CMS is a detector. We're a collaboration. There's about 3,000 of us PhD physicists that work together. We sign all the papers. I just had to do my annual review for the department. I had to update my Vita.
That's ridiculous.
I learned that I had 150 publications last year in the process of doing that.
Yeah, we need to dive into that one later because that
we can talk about the sociology of high energy physics. Is also a very interesting. It's an experiment of a different color, as a matter of fact.
Yeah, no, that's a behavioral question right there. All right, we're gonna put up the prediction right now. If you guys have a guess, the diameter of the CMS detector, so it's the particular detector that Ted works on, is it 1.5 meters or 15 meters? So those of you in the United States that don't know what these means, 1.5 meters is what, 5 foot. 6
meters, like a yard, right? It's close to a yard.
And then 15 meters, yeah. I'm just going to do the translation. 15 meters to feet. That would be 50 feet. So the question is, what is the size of the detector? Click that predict button. Make your predictions right now. Make your guess. Don't use ChatGPT, although we could check again whether that's going to give us the right answer. Man. 150 papers in a year. Obviously, you proofread all those.
I proofread some of them.
Yeah.
I read a few more. Haven't read all of them. It's weird to be in the situation where you've written way more papers, quote unquote, written way more papers than you've actually read.
Yeah, I was going to say, because like, how do you find a reviewer for that when everyone involved is on the paper?
It's difficult. You know, like for tenure, you're supposed to have letters from people who aren't your co-authors. Well, good luck, because everybody in the field is part of either our experiment or our direct competitor, which isn't much better from the perspective of like independence. But, you know, we're so far above the like Dunbar number, right? This idea that like humans can only foster like 150 or so like actual relationships in their lives.
Yeah.
That there's lots of people on CMS that I've never heard of. So the fact that we happen to be co-authors in this very particular sense doesn't really mean a whole lot in terms of...
Do they actually enforce that for tenure letters for you guys? Or do they just need to list their connection or possible...
So it's not an absolute requirement, and in our field, I think it's pretty standard that people will get maybe half their letters from people who are co-authors, because those people will also know your work well enough to comment on it. You know, in a lot of fields, you would have sort of a group of people you would run into at conferences and stuff that wouldn't be your co-authors, but that would know your work. But those people are my co-authors. Like when I go to a conference or a workshop, it's generally like a lot of CMS people there. So yeah, I think half of my letters from people on CMS and the other half from people outside of it.
No, that makes sense.
Yeah, I mean,
as long as they
explain
the connection, it's not an issue. Like that's not uncommon. So we're an hour and 15 in. You want to keep playing? You want to switch to something else?
I think we should switch. I think we should switch games. I'm going to finish picking this.
Oh yeah, by all means, finish the round
here.
Just give you an estimate of the time, because time flies.
Time does fly. I always feel like it's going way faster than I'm like, how are we going to fill the time? And then we're almost halfway done already.
Then it's time to play NARC. Then you're super focused.
Uh-huh.
I can't remember. Did you beat Rachel on your time? I think you did.
I would have to revisit that. I mean, it sounds like I would have, but I don't know for sure.
She wasn't, I think she played Pac-Man when she was on.
Yep.
But we're going to have her on in the summer or the fall, so she'll get a revenge or a rematch on that one. Oh, man. Speaking of which, you guys are around May 7th for the Ask a Scientist party?
I was just mentioning that to her before I left, so I think we'll come.
Man, it's going to be interesting. I sent an invite out to 150 faculty.
So that's people that have either done the event at Railroad Square or been on this stream.
Mm-hmm.
Cool.
It's 150. Yeah, it should be fun. All right, I'll go. So you're going to pick another one?
Yeah, so I'm going to play another kind of puzzle-inspired game here called Slipways, which is probably even easier to grok than Balatro.
No worries. That had 1,500 viewers. That's a non-trivial amount. So when you play at home, do you play on a screen or do you use the handheld?
I haven't had that many opportunities to use the handheld, actually. I don't know why this is... One thing that's nice is that, so I have like a proper PC in my house, and you can stream using Steam streaming from the PC. So if you're playing like a game that requires like the full abilities of the desktop, you can like go in the study or whatever and play on the handheld, which is the main reason that I bought it, to enjoy that functionality. But
yeah. All right, there we go. We're on Slipways. I have to turn that one down. You guys will have to let me know if it's too loud. It's got some sound effects. I like it. So what is this game? Space travel, alien warfare?
yeah, so this is like it's like a economic empire building game. So you basically, you have planets that you connect by the titular slipways. And the idea is like each planet like wants some resources and like produces some other resources when its needs are fulfilled. Then it like upgrades to be a better planet. And the idea is you have a certain fixed number of turns corresponding to 25 in-game years, and the idea is to build the best space empire that you can during that time. So to start with, I need food, because you can't have people without food. So I got to find some planets to make food, and then that will get me started building people, and you'll see.
So this was Slipways? Is that what it's called?
Slipways, yeah.
Let's see how many people are playing Slipways right now.
I'm curious about that too.
There are 666 followers, but it doesn't look like maybe a couple are playing.
Okay.
Balatro. I don't think I'm going to stream via that one. So this is Age of Empires Space Edition.
Something like that, yeah.
I like it.
So yeah, here's an Earth-like planet. So if I can get food, I can make people. So I'll tack this.
Man, I'm kind of upset you can't have like one of the CMOS detector. I don't know what detectors you guys use, but just like a keychain of previous CMS detectors. Like, man, that'd be so cool.
Well, so we're reaching the end of this rather large effort at FSU to test a lot of silicon sensors that will go into the detector. I guess there will be some kind of like cutoffs and stuff. Like,
oh, that's fun.
Structures that were made by the producer to try to like prove that the quality of the sensors is like sufficient to be installed. So I hope that we can build like a little sort of museum, a little display in the department, like showing what these sensors were like, because then they'll all get installed in the experiment and no one will ever see them again, which is kind of sad to contemplate.
And just the value behind it. All right, Ted, what's the answer? 1.5 meters or 15 meters?
Yeah, so the diameter of the detector is about 15 meters. And as I said, our competitor experiment, Atlas, is even like another factor of 2 or 4 larger than we are. So there you're talking about something which is really the size of a football field if you're American, or pitch if you're European.
That's crazy.
About the same size either way. But yeah, so the reason that it's that big has really to do with the necessity to identify the different particle types. And the main resource that we use to do that is that like different particles can travel a different distance through material. So muons, which are sort of so interesting and so important to what the experiment does, those particles can traverse a lot of material before they interact, just by the interactions that are available to them. And so if you surround the interaction point with like 15 meters of metal, which is basically what we've done, pretty much muons, as well as neutrinos, which we can't really detect at all, but muons are pretty much the only thing which is able to traverse all of that material and still be moving. And so the size of the detector is largely set by the ways that the particles interact with matter. And so yeah, in order to screen out everything besides the muons, we just build it really big so that we can have lots of absorber in there, in between the interaction point and those like muon detectors. And that's why it's so big. But then there are also parts of the detector which are incredibly small. So this pixel detector, which is used for measuring distances on the order of like microns near the very center of the experiment, is tiny. The whole thing is just the size of like a couple of beer cans end to end, and there's like 100 million channels in that tiny thing. So really, we printed t-shirts at some point that said fine precision at a massive scale, which is an interesting way of thinking about the challenges involved.
Fun pitch.
There's a famous picture from the detector upgrade that we're working on now that shows the smallest screw that we have and the largest screw. So we have these metric screw sizes, like M1 is 1 millimeter. So we have everything from like M0.5, so a 0.5 millimeter screw, which you can like barely see the threads with your naked eye. And then we have an M30, right? So it's like a giant bolt that holds up like tons of metal. And you put these things next to each other and you realize you have to have parts of both of these sizes and sort of everything in between in order to build a really huge detector like that, but that has the ability to make some really tiny and very spatially precise measurements at the same time.
I mean, so you're stacking, you said there's a thickness to it, right? To get enough collisions to actually see it, but you're stacking detectors upon each other, and each one you have a readout from it, right? But you only see it when it actually interacts.
So CMS kind of looks like when you like tie up a pot roast into kind of like a cylinder of meat. CMS looks a lot like that. CMS is roughly cylindrical, and it has this geometry where the central part of the detector has these cylindrical rings surrounding the interaction point, and then there's what we call end caps. The part that we're working on the upgrade here at FSU is going to be the end cap calorimeters that sort of plug in from the ends. And you want to be as hermetically sealed as possible, because even though we can't detect neutrinos, we can infer their presence, because even though all this crazy quantum mechanical stuff is going on in the interactions, momentum is still conserved, right? So you can infer the presence of a neutrino if you can measure every other particle in the event and they don't add up to zero momentum, then you know that there must have been some other particle escaping which was not detected that carried that momentum away. Now, if you have a gap or a hole or a crack in your detector, that could be anything. But if the detector really fully surrounds everything and there's no gaps, no cracks, I mean, we can't really have no cracks, but we can minimize them as much as possible, then it makes it much easier to interpret this missing energy as the signature of a particle.
That's fun.
Which did escape.
You rely on energy balance. Like the math has to check out, right?
That's right. Yeah. So like, even though it's, the same thing that you do in like basic first year physics to like, see if there's you can solve for a collision between train cars or whatever using the conservation of momentum. It's really not much more complicated than that.
Laws of thermodynamics.
So yeah, this huge size has to do with, you want to have all this material, and then you also need to be able to build it in such a way. If you were just trying to measure particles escaping at one particular angle, which is like how they used to do physics experiments, different people would come and surround the interaction point with all their own detectors, but they wouldn't necessarily be connected together. They wouldn't necessarily talk to each other.
So they'd each get their own story.
So then it's easy, right? You can just put your station 15 meters away, and you don't necessarily need all this other like support structure, but then you're also completely insensitive to these variables that require you to measure the whole area. And as a result, the field has really been driven in the direction of these very large general purpose detectors, such that essentially all particle physics experiments at colliders, some of the details of the technology that they use is different from case to case, but the general concept that I've just described of how the detectors are put together, that's pretty much universal at this point. There's not really any other ways of doing it that people are actually doing. And if we're one of the things we're talking about in the field right now is like, what should the next accelerator look like? We talked about how electrons aren't very good candidates, even though they're an elementary particle, which is good. They radiate a lot. Well, it turns out there's another particle which is available to you that you could use, and that is the muon.
Oh,
Now,
interesting.
muons are not totally stable, but they're pretty stable on the scale of subatomic particles. And as you get them moving faster and faster, your special relativity helps you. So the faster a muon is moving, the slower its clock runs relative to the observer in the lab. And so the longer distance it travels in the lab frame. And so people have an idea that if you can get the muons accelerated fast enough, you have just enough time to bunch them together and accelerate and collide them before too many of them decay.
How do you control an accelerated muon?
So it's a charged particle, just like a proton or an electron, and so it obeys the laws of electromagnetism just pretty much the same way that those other particles would, just with the caveat that it's much heavier, and so it tends to radiate much less, which is exactly what we want in this case.
That's pretty cool.
But there's, of course, all kinds of problems that come along with that. Like, many of them will survive long enough in order to be able to collide, but not all of them. So you have this constant decays in flight of all these muons, which is producing actually like a collimated beam. When a muon decays, one of the things it decays to is muon neutrinos. And we don't normally think of neutrinos as being damaging, but if you have, billions upon billions of muons all traveling in the identically same straight line, you actually have an incredibly bright beam of neutrino radiation
muon laser
shining in the forward direction. Yeah, exactly.
Don't shine it in your eye.
And it's kind of like in the danger zone where it's, because there's so many of them, they do result in a measurable amount of radiation, but because they travel through 10 light years of shielding or something on average before they interact, there's not really any way to screen them out. Wow. So you have to think about where you put this thing, and particularly where, if you have a straight section of the detector where all these muons are going to be traveling together and decaying, you don't want to have Bob Smith's house at the other end of that line, because he will get a huge flux of neutrinos.
Oh my God.
That could actually cause some kind of...
You see the moon light up at the right...
Exactly.
I like that. That's awesome.
Exactly.
All right. Misadventures in Astro, welcome back. Thank you for joining us. Misadventures has redeemed Take a Drink. So, Ted, are you good? Do I need to get you another?
I'm still working on this one.
Cheers, Misadventures. Hopefully I have a drink in hand. We're celebrating the 100th stream of Ask a Scientist Gaming while hanging out, talking some high-energy particle physics, and playing some Astro in Sideways here. Playing some Astro farming right now.
So this game has a kind of a deliberate... pace, but what I'm trying to do is identify which, so these products which are lit up are not currently being used. So for example, I have two guys here that I could send, for example, to adjacent planets to do maybe some useful work for me. So for example, this Arctic planet, if I give it green biomass and yellow food, it can produce two people, which I probably don't need because I have people here, but it can also consume robots, which I have here, to produce water, and then maybe there's a planet around here which would want to use water for something.
So does this end up being space warfare? You're taking on other people to occupy space?
There's no other. It's again just like a solitaire. There's no violence. There's no warfare. Just trade. I hope it's how the real space colonization ends up going.
So naive. We learn nothing. History has told us anything about human behavior.
Kids and I have been watching this show it's on HBO Max. I don't know what actual network it airs on, called How the Universe Works, which I hadn't seen before. There's many seasons of it, and it interviews astronomers and other physicists and stuff. And each episode kind of has a different topic. One of them was they sent a crash test dummy. I mean, not really, but they animated him going through space and encountering all the horrible ways that he could get destroyed, by falling into a black hole or getting fried by space radiation or whatever. And they had one about basically solutions to the Fermi paradox. Why is it everything we learn about the universe seems to indicate that life the conditions, the kinds of planets that we think life would want to arise on. This seems to be not a rare thing, like at all in the universe, that there are actually many such planets. And basically with every passing year, we discover more and more and more exoplanets that many of them are in the like habitable zone of their stars. There should be liquid water. Life emerged on Earth like pretty much right away as soon as it was cool enough for like chemistry to happen. And so unless there's something super special about Earth, and the kind of Copernican principle suggests that we shouldn't be that special. I mean, maybe we are, but we don't have like an explanation for why we should be so special. So then that tells us that probably there is a lot of life out there. So there's got to be like a filter somewhere that's preventing, not every star system surrounding us is like broadcasting television and radio signals. So there must be something that happens that prevents like basically every solar system from having a civilization like ours in it. And it's interesting to speculate about what that might be. So I thought this show actually did a pretty good job of tackling that on a level that was like understandable to, like a kindergarten age kid. So if anyone has kids that age, I'd recommend checking the show out. I thought they did a pretty good job.
Man, I love, in historical context, our non-uniqueness. Like, all we've done from the start of scientific progression is to knock humans off to their pedestal of independence. And it's like, I'm of the position that alien life is I mean, necessary at some point, right? It's an inevitable outcome of just the rules that dictate formation of bonds and whatnot. So, no, I'm all about that position. But it is intriguing to think we should be hearing some noise, right, from these. If they're functional, if they're communicating electronically.
It's a little bit unsettling in a way, right? I mean, some of the solutions to the Fermi paradox are not very nice. Like maybe there is something scary out there that everybody else is smart enough not to broadcast to, and we just haven't figured it out yet.
Yeah.
There's a lot of science fiction that has fun with this idea of like what could be the reason why. It's too far.
And my daughter, so she's in second grade. She started bringing home these like, aliens and Bigfoot and all that. Like there's a book series, but they're like an honest, like, here's what some people think, but it's probably this, and so on and so forth. And I really appreciate that. But brings me back to my childhood and potentially yours. Unsolved Mysteries.
Oh yeah.
Wasn't that amazing? Bigfoot was real and was going to be looking in your window. Bermuda Triangle, obviously you shouldn't fly through.
Is that the one that had Jonathan Frakes as the host? Or was that
Jonathan Frakes was, I can't remember. Who was
you know what I'm talking about?
Yeah, I do. Yeah, that was a later one. Unsolved Mysteries was Alan Stack. Unsolved Mysteries. Who's the host of it? Can't remember his name. They brought it back on Netflix, but it's not as much fun. Robert Stack, there's his name. So Jonathan Frakes. Yeah, that guy. What was the one that Jonathan Frakes? Jonathan, what shows did Jonathan? Beyond Belief, Fact or Fiction.
Fact or Fiction, yeah, I remember that.
Yeah, it was a similar strategy, right? You play the mysterious music and then you show some unknown thing and it could be the XYZ.
Yeah, I mean, now as an adult, I realized that these shows were probably popular because they cost the network, like basically, you just have to hire like one guy.
Exactly.
You have some like really cheap like recreations that has like a shadowy figure in the dark with like a flashlight or whatever, so it also costs like $10 to make. And then
super ominous, and then voiceovers, and
they would repeat the same like clip like at the end of the previous like, and then the commercial break, and then they would start by showing it again. So like you only need to generate like half as much actual content at the time that you have to fill.
But man, I loved them. I don't know what it would be like watching them now. I might have to relive that with my kids, but that's fun.
All right, so this Slipways game for some reason is running at a resolution that makes it really hard for me to see what's going on, and I don't seem to be able to change, but this is also a really difficult map that I ended up on, so I'm kind of inclined to just punt on Slipways and move on to the next thing that I wanted to play.
What's that?
Which is going to be Assassin's Creed Shadows.
All right,
we're going to plug in the PlayStation here.
PlayStation 5 time. Is this the latest Assassin's Creed? I haven't kept up.
It is, yeah. I haven't played all of them, but for me, this is like comfort food.
Assassin's Creed Shadows. Let me update our title. I mean, it's just such a fun game. I love the mechanics behind it. You know, jumping off a tower, landing in a bushel of hay, being fine. All right. Hopefully this recognizes immediately. We're switching over HDMI, so hopefully the screen is gonna...
Well, now that we learned the HDCP trick. Yep, there we go.
Awesome. So I'll let you get up so it doesn't show your ID or whatever might be looming behind the back. But yeah, if anyone has questions for Ted Kolberg, he's happy to answer them. We're talking about Large Hadron Collider. We're talking about particle physics, smashing things into each other really fast and really a lot of times, 1 billion times per second. Yeah, if you guys have any questions, throw them in chat while we transition to Assassin's Creed Shadow, which I'm excited to watch some gameplay. So speaking of, so if you could accelerate electrons, I mean, colliding electrons has to be hard, right? Just like sheer size. How frequent would those collisions versus proton collisions be?
Yeah, so it's true that the like cross-sectional area of an electron is very different than a proton, but the idea of how to collide them is not so dissimilar. I mean, unlike colliding macroscopic objects, where if you have like a car and another car, and you like put them through the same region of space, they're virtually guaranteed to actually come into collision. Here, just most of the time, the beams are going to pass through each other without really anything happening. So the collisions are going to be rare. And the way that you overcome that is basically by just packing a huge number of them into a small space. And luckily, when these particles are moving fast, the electromagnetic like forces on them from these steering magnets that you have are actually incredibly strong. So it makes it, you know, maybe you remember from physics this idea of like the Lorentz force, that when you have a charged particle which is moving through a magnetic field, it feels a force which is proportional to the velocity. So here we have the velocities are very, very close to the speed of light, like 99.9999 times the speed of light. Percent of the speed of light. And so the forces on them are actually quite strong. So basically you build a special geometry of magnetic field that takes an already tiny bunch of particles and funnels it down to as close to like a point as you can. I think the size of the luminous region will be measured, you know, it's a Gaussian thing, so it has some tails, but like the core of that luminous region is brought to like a very small size at the interaction point. And then you just sort of rely on the sheer number of particles in the stream to do your work for you. So, you know, when you collide two bunches, they're almost completely unaffected by the collision. You know, we will keep the same bunches of particles in the LHC for like 24 or 30 hours, just colliding continuously.
Just over,
and there is some loss of the particles over that time, but mostly not due to the collisions themselves. I mean, that's a contributing factor. Some particles kind of leak out of the magnetic fields that you're using to steer them. So it can be, you know, the better you design your accelerator, the longer you'll be able to keep things in there before all the particles go away. But basically you just put like many orders of magnitude more particles than are ever going to collide. And then you just rely on the fact that even though an individual collision is very unlikely, there's just so many particles involved. I wish I could remember off the top of my head the number of protons in a typical LHC bunch.
To get that billion collisions, that's interesting.
Yeah.
So there are 5,200 people playing Assassin's Creed Shadow right now.
On Twitch?
Yeah.
Well, now there's 5,201.
Mediocre gameplay, expert science. Misadventures has a question. Let me copy this so we have it for the record. All right, I'd love to hear Dr. Kolberg's thoughts on Sabine Hossenfelder insistence that large colliders have been nothing but a waste. Ooh.
Yeah, so I've followed Sabina Hossenfelder for a long time through her blog and now her YouTube channel. I've read most of what she's written over the years. I think she's a smart person. I think she's a person who feels somewhat burned by her experience in academia, so I think she doesn't have the most charitable view. But in some sense, I think she's right. I mean, it is true that the dynamics of science funding and science, especially like mega science projects, really do incentivize people, I think, in many cases to overstate the likely outcomes of their research. And this is not something which I think is very particular to particle physics. I mean, I think anybody who's written a grant is familiar with the temptation to gild the lily a little bit in terms of how impactful the actual, the big picture of particle physics, I think, is about as impactful as science can be. I mean, what is science for if not to understand the truly basic, what's sort of a more worthwhile pursuit in science than to understand like the basic building blocks of like matter and forces? I mean, to me, it's self-evidently important and worthwhile to try to unravel those mysteries. It is also true at the same time that many of the promises that were made by people trying to get the LHC built and funded have not come true. I mean, people used to talk about supersymmetric particles pouring out of the LHC, and that the main problem would be to identify the spectrum of all these different, could we disentangle all the different new particles that were being produced? People had quasi assurances that that like dark matter particles must be within a mass range which is accessible at the LHC. And if that is true, it still might be true, but there's got to be some kind of, the story's got to be a little more complicated because we haven't found them, at least not in the simplest types of scenarios. So have people exaggerated the likely outcomes of the research? That's certainly true. I'm not really sure, though, what she thinks would happen if we, like, canceled the LHC. I mean, I think a lot of people have the temptation to think, oh, if we cancel one of these big mega projects, that will lead to all that money, like, flowing into my own pet. Hey, that wasn't nice. Guy rejected my assassination attempt. Didn't used to happen in the old games.
No, they had that option.
Well, if you go from the back, they can't. But if they see you coming, they have a chance to stop it until you unlock like another skill that then prevents them from doing that.
I mean, that's I mean, she's essentially talking about return on investment, right? Like, what's the either scientific or financial profitability of any pursuit? And that has a timeline, right? Like, it's disingenuous to say after 5 years this was unsuccessful. I mean, especially with fundamental physics. And like the best example, or one of the ones I like to do, is Einstein's relativity, right? Just figure out how the science works, and then 100 years later you're going to have GPS, and it's awesome. Like the insights, I don't know. But I guess, is the argument that it would be better spent elsewhere? Is that her central focus, or that it's just a waste of time entirely?
I think she's offended on an aesthetic level by people claiming that things are going to happen which don't end up happening. Like, fair. I think it's fair to feel a little bit misled and a little bit like lied to, that people have made great promises that all this, that, and the other, like new physics signatures, whatever, will pour out of these machines. Mm-hmm. But I would be lying if I wasn't also like a bit disappointed. I mean, I did not think when I was like embarking on the adventure of like joining this field that we would discover so far the Higgs boson, which is a truly momentous discovery, and we shouldn't undersell the importance of that. Like, I think the Higgs mechanism is a truly like interesting and remarkable thing in the history of physics, and like the fact that this scalar field that suffuses everything is responsible for breaking this electroweak symmetry, and that we could detect the excitations of this field as like a particle in our experiments, I think is truly remarkable. A really fundamental discovery about the world that really changes something about how physics works. But that prediction was also made like 40 years ago, so people have had a lot of time to like adjust to it. The long time scales involved, I think, don't do the field favors in terms of the kind of like newsworthiness of the discoveries. I mean, the Higgs boson discovery was definitely a big deal, but I think it would have been an even bigger deal if the theory had been generated like closer to the discovery, right? Having so long to think and talk about it in between when it was first suggested and when we finally like realized that it was actually true. I think people kind of priced in after a certain point that there must be a Higgs, and it was just like, what's taking so long to find it? Which, I don't know. I think it would be great if we lived in a funding climate and just a general like informational environment where academics and experts of all kinds weren't constantly feeling the pressure to overinflate claims and to be salesmen and could just focus on the science part. But it's not the world we live in.
Sabine should not read a chemistry journal where it says, this material is promising for X.
I think like most of what she says is right in terms of the failure to deliver on certain promises. But in the end, I just don't find it as like disturbing or distressing as she claims to. And I think, again, there's an element of like the way that her career went and like her adventures in academia ended up for her was probably very unsatisfying, and I think it's hard not to let that color a little bit your idea of the field. But
in her defense, it's easy to get jaded in academia, especially if you've ever served on a grant review panel, and it's like, how does anyone pick money, and why do these people get money and awards and I don't? And I feel the frustration.
So and the hugely collaborative nature of the field and the fact that these experiments are so big and they take so long and there's so many people, I mean, there are definite upsides and downsides to that. I actually think that the physics case for something like the HLLHC has been worked on by a huge number of extremely smart and talented people over the course of decades, in a way that like a lot of research doesn't actually have as huge of a, the volume of things that people have written and calculated over the years to explain and motivate why we might do these upgrades to the LHC. Like, we really have thought through a lot of it, and I think there's a lot of research which is not nearly as well supported. So, is the HLLHC really likely to generate a huge surprise of like some new type of particle that we weren't anticipating? I don't know what odds I would put on that. I wouldn't bet even money that we would discover supersymmetry, but it's certainly a possibility. How much is that worth in like dollar terms? I mean, that's a really hard question to answer. But part of me feels good to like live in a society that tries to do things like build the LHC, even if not every prediction comes true. I don't think that we should so casually reject the idea that it was still worth doing.
Also, in defense of all this, there's underlying things that must be developed to do these measurements, including detectors and light sources and all sorts of things that manifest in electronics after some period of time, or silicon processing, or whatever.
And it's also just like a
tangential byproducts.
It's a little unfair to like make the judgment like after you know the answer. Like sure, now that we've done the LHC and like haven't yet discovered supersymmetry, it's easy to like point at specific predictions that some people made and say this was overblown, this didn't actually happen. But like a lot of smart people thought there were good reasons like why it might, or even that it was more likely than not. And I don't think that can all just be explained away as some sort of like scam that people were running. I think the people that were making these predictions were in some cases, really brilliant people, certainly most of them much smarter than me, and that they were people. It's hard to make predictions about fundamental physics that you haven't discovered yet, and we shouldn't be so surprised if people get it wrong sometime. And I'm not even sure we should hold being wrong in that way like against the field or against people. It just seems like a little bit of an uncharitable.
In retrospect, it's easy. So where was she when it was first being built? Was she still oppositional to the LHC?
That's a good question. I mean, I was in like 6th grade when they were first conceiving of the LHC. And she's probably a little older than I am, but her scientific career definitely doesn't date back that far.
I see.
Either. It's a good question. And I think, we shouldn't be afraid. Certainly, we shouldn't be afraid of people making criticisms. Like this idea that scientists should somehow all speak with one voice on these subjects, and that like we should try to tamp down any like criticism or controversy. I think that idea has actually done a lot of harm to the way science is like talked about, especially in like the popular press. This phrase like follow the science always like bothered me, because science is like an argument. Science is not like a set of facts that all scientists can agree on. I mean, there are some facts that probably most scientists can agree on, but very little scientific research is happening on those things just sort of by their nature, right? Scientists aren't people who just exhaustively reconfirm and catalog the same like few things that everyone agrees on. People are trying to new things, and it's not always clear if an experiment was like successful or not, and like the evidence can be subtle and difficult to interpret, and some amount of disagreement I think is super healthy. So I welcome Sabina Hassenfelder's criticisms. I think people should read them and take them seriously, but that doesn't mean they necessarily have to agree with all of it.
Misadventures. Nothing ever gets funded with realistic promises. Sabine obviously never involved with a business investor. All right. Maximinus, without colliders, how else would you study physics of high energy scales? Ooh, that's interesting.
That's a really good question.
Wow.
So there are some efforts to do that. Actually, the way high energy physics started, we didn't have accelerators, and people were just looking for new particles in mostly in cosmic rays. So there's a source of very high energy particles that reaches us basically for free, that are cosmic rays. So the Earth is constantly being bombarded from outer space by super high energy particles, and actually some of the particles in that bombardment are way higher energies still than what we can produce in accelerators on Earth. So there are still experiments like the ice cube experiment at the South Pole is a giant detector like buried in the ice of the South Pole that is just sitting there like waiting for, in this case, super high energy neutrinos, PeV. So yet another set of 3 orders of magnitude higher than the energies of the LHC, particles that will just, with a low rate, but they just come from the cosmos, and we can look at those interactions, and there's some really interesting stuff we can learn about the universe. I don't think we fully understand like what processes in the cosmos are giving rise to these super high energy cosmic rays. Like it seems like there might be some kind of dynamics of like active galactic nuclei or something, or quasars or something, that are producing these high energy particles, and there's probably something we can learn about the cosmos from cataloging like where they come from, and trying to learn more about their spectrum and like what direction in the sky they come from and stuff. Another thing that you can do is not go to super high energies, but go to super high levels of precision, and in some ways this is just a different way of attacking the same problem. So one way to discover a new particle is to produce that particle like at rest in the laboratory frame in a high energy collision. But actually, like any process that we look at, if we can be precise enough in the measurement, it will turn out that processes which occur at a much lower energy can have contributions from higher energy processes subtly inflecting the results of the experiments. So there's a whole field called flavor physics where we intentionally don't push for the very highest energies, but instead we try to increase as much as possible the number of particles that we produce and look for very rare decays, for example, of those particles, or even just slight modifications of the rate of decays that we know about. So it doesn't even have to be a new process. It could be an existing process, but it's just one time in 10 to the 10th or something, it turns out a little differently than you would think, or the like momentum of the decay products even is like distributed in a slightly different way than we would have thought. And so that can be another way of attacking it. In most cases, those are still accelerator based, but not necessarily accelerators at the very highest energy frontiers. And then, frankly, there are people who think that we can just use like raw brain power and like our ability to write down mathematical equations to make discoveries. And some discoveries in physics actually have this character. So like general relativity, as far as I can tell, when Einstein was writing down general relativity, there wasn't any like experimental fact that he was trying to explain. It was just like he was so smart that his brain could just like conceive of this whole explanation of how the world worked basically from first principles. And there might be people around that are still able to do that. So it could be that just an idea can actually unlock a whole field of physics even without, I mean, people later went and found evidence of general relativity, but I don't think that he was trying to explain any particular experiment. He just like thought really deeply about like what the implications would be if the laws of physics were a certain way, and his intuition was able to guide him to a theory that we now recognized not only as true, but as like the whole basis of like how we understand the evolution of the cosmos and stuff. So I think like it's always hazardous to predict that there will be like another Einstein. Physics has changed a lot since Einstein was doing his stuff, and maybe it's harder now to have that level of insight, but I wouldn't rule it out that someone could just use like sheer brain power to like unveil truths about the cosmos. I mean, that would be pretty cool, right?
Yeah.
To have another Einstein type character revolutionize our idea of physics.
When was the last time we had that?
Probably Einstein.
Yeah. Well, Einstein and the early quantum, right? That was the main paradigm shifts.
Yeah. I mean, with quantum mechanics, there's a slightly different situation because there were things like the like ultraviolet catastrophe, right?
Yeah,
so
there
like
were
the
gaps.
spectrum of radiation coming off of a hot object. There were like certain theoretical problems, like classical physics did not return like a sensible prediction for how much radiation should be emitted by a hot object. And so there was like some indication there that there must be some, I think many people around the same time had like ideas that were fed into the development of the quantum theory just because like there had to be something there. But general relativity, I don't think was really like that. Like it was just much further ahead of its time. I don't know of another example really like Einstein. I mean, Newton in some sense, I think was like this super galaxy brain individual who like saw hundreds of years of physics like clearly in the mind's eye and was just able to in some sense like write it down.
Yeah.
And like Einstein, also Newton also had some like kind of weird ideas about the world, and he was like into magic and alchemy and all this stuff, right? Just the same way that Einstein could never make peace with quantum mechanics because it just didn't feel right to him that that's the way the world should work. So this business of like doing physics by gut feeling, I think also has some serious drawbacks that you see even in the most amazing practitioners of the art form, that there was some, your intuition, even if you're as smart as Einstein, your intuition can still lead you astray.
I mean, so if you had to put a guess on it, like what would be the next physics Einstein moment? Like it would obliterate the standard model and create something new. I mean,
one thing
obviously, if you knew, you'd do it. But like, could you speculate on where the failure is going to be, or where the new foundation will be?
I mean, sort of by definition, I think these things tend to come from unexpected directions. But if I could think of like what are areas in physics where it seems like we should be able to make progress, but we're just lacking like an idea to do so, I think quantum gravity is one example. So like we pretty sure most physicists would think that there should be like a quantum field theoretic description of gravity. I mean, it's a force. We can describe all the other forces in terms of quantum field theory. And so like, why not gravity? I don't know of a good argument why gravity like shouldn't be able to have a quantum field theoretic description, but there are certain technical problems. This is not exactly my area of expertise, but there are certain technical problems that mean that like there is kind of a program that people are following, but they don't necessarily expect to come to any understanding like anytime soon. It's like a project on the course of like decades or centuries, not on a course of years, to write down a quantum field theory of gravity. But that's exactly the kind of problem where I would think if there's some genius kid being like born right now in Africa or whatever that's going to like have this crucial insight that like allows you to make progress on that question. So that's one possible place it would come from. And then I think that we are living right now through all of the promises that the LHC arguably hasn't revealed as much, let's say, about dark matter as we might have hoped. I think the early returns from like the James Webb Space Telescope, from what I can tell, again, not being super, this is something that I follow as a fan more so than an active physicist, because I'm not really a observational astrophysicist, but like my understanding is that we've had this cosmological standard model for many decades that was kind of patched over to accommodate new facts, but seemed to hold up pretty well. And the stuff that's coming out of Webb as far as like the structure formation in the early universe just does not seem to fit the picture that people have had in their minds for decades.
That's fun.
And when you start looking around at how much of physics kind of assumes that this is true, I think that could be an occasion that would cause like a great I think there could be big consequential ideas coming in cosmology that are going to be kind of unlocked by the idea that these results from Webb are just really not coming in the way that we thought. I think it's really stretching the bounds of the standard model of cosmology to explain why there's so many huge galaxies so soon after the Big Bang. I don't think anyone really expected that. And even the traditional alternatives to dark matter, like lambda CDM cosmology theory, like modified Newtonian dynamics, is an idea that some people believe is like a valid alternative to dark matter. But I don't think that it does any better with these cosmology things. So I'm guessing that there's like a big idea out there to be grabbed, and some smart person's going to come along to grab it sometime soon.
So I'm going to play Sabine on this one a little bit. So if you had to go back in time knowing what you know now, and you have to choose between the LHC and the Webb telescope, you have to fund one of those two proposals.
Well, that would be a difficult choice. The amounts of money involved, I think, are sort of broadly similar.
Yeah.
But we're going back. You're saying I'm going back knowing what I know now.
Yeah. Knowing what you know now.
Well, then we don't have to build either of them. I can just tell everybody the answer. I would be the genius that would totally revolutionize physics.
Here's what will
the Higgs
happen.
boson at 125 and like lambda CDM is wrong, and like you go ahead and build the experiments if you want. But
It's all fun and games till you get institutionalized in electroshock therapy because you're a lunatic.
Right. I mean, you get emails sometimes from these people who are like,
man.
I have the new theory of physics, and if only you would just listen to me. Like, I rate it as unlikely that that's where the next breakthrough is going to come from, but not literally impossible. I mean, it could be.
Man, the favorite one I got was, I'm a color chemist, right? But I got this mail to my office at work. It was, the organs have colors, and if you can match the color resonance with the wavelength of light, you can heal, and it was just off the rails amazing. I kept that one.
Big if true.
Exactly. Scientists don't want you to know or solve physics with this one trick. Get Galileo'd.
As usual, the sort of conspiracy theories, I think, reveal more about how poorly we've explained to the rest of the world, how science actually looks and works. If I could rate a group of people that was least likely to be able to pull off some kind of a big conspiracy, I think physicists, scientists would be like high on the list. We're people who generally love a free and unfettered exchange of ideas. We're people who are generally really interested in unusual and bizarre theories to a point. I mean, if there can be some connection to the real world, I think we're generally very open to those things. And the idea that we are all kind of like closing ranks against outsiders is, it's hard to acquire the necessary knowledge to even like have the conversation, right? So it's not for nothing that people feel like they're being excluded, because there is a lot of information you need to master before you can even like really enter the conversation. But yeah, I think the idea that we're like out to, we would love it if some smart person came along with like a theory that solved our problems. It's just that normally these theories aren't nearly as explanatory as the person coming up with them seems to think.
Actual Education with the raid. Actual Education, thank you as always. Thank you for joining us. You guys should check out Actual Education stream. Does free tutoring of math and science, which some people, as we're discussing, could use some of that. Organs don't have colors. Likewise, you're not solving things on the back of your... Anyway. But yeah, Actual Education, thank you for joining us. Is he talking about Terrence Howard? What was that?
Basically, yeah.
1 + 1 is 3. What was
I tried to understand what he was talking about. I really just could not understand.
But actual, how was your stream tonight? How is it going? There it is. 1 × 1 = 2. Endar, thank you very much for that. Recky Rec, thank you for joining us. We're Ask a Scientist Gaming, mediocre gameplay, expert science. Every 2 weeks we have a guest on with different expertise who plays some of their favorite video games. Right now our guest is Ted Kolberg, who's an expert in high energy particle physics. He works on the Large Hadron Collider, in particular the CMS detector. So we will talk about smashing particles into each other very fast and trying to describe the physics of those things while playing a little bit of Assassin's Creed Shadows.
Yeah, I just want to take a minute to appreciate how amazing this game looks. Like, you saw from the other games that I picked that I'm not like a huge snob when it comes to graphics. So this is a PlayStation 5 Pro that this is running on, so it has like real-time global illumination running at 4K 60 frames per second. I mean, you guys, I guess that's maybe not coming through fully on the stream, but this is like one of the coolest looking games I've ever seen. This feels like a real like generational leap. This like ray tracing stuff, they're figuring out how to like use it in concert with the art direction, and I think it looks spectacular to me. I mean, it's like you can see the light kind of filtering through this like haze in the trees, whatever. Like this game is full of little moments that I think are just like a pleasure to look at. It as someone who's not particularly into like graphics technology, I just find it like utterly captivating to watch.
I like this mechanism for leading you. Like, it's not too obtrusive. It's there, but it's obvious. That's kind of fun. But so earlier we were streaming from the Steam Deck. Have you streamed to like your monitors? Does the resolution look low, or was that an issue with our connection?
No, it outputs at least a 1080p. I don't have it like plugged into a really high DPI monitor at home. I have a projector in my office that usually it's plugged into, so I can project on the wall, and that's at 1080p, and it looks just fine there. So I'm not sure what that was.
Yeah, that might have been my settings. I didn't actually look into it, but so it goes. Well, thankfully we didn't need it for a card game. But yeah, this does look beautiful. I'm glad you're playing. But yeah, if you guys, anyone that's joining us has questions for Ted, he's happy to answer them. Ask anything you want. We talk about, wow, we've been on a bit of a journey. We talked about the cost effectiveness of funding high dollar amount physics, whether it's the Webb telescope or Large Hadron Collider. We talked about CMS detector and number of collisions per second and why you might want to use electrons or muons.
I mean,
instead
luckily,
of protons.
Funding high dollar science is after today not going to be much of a problem anymore, because my understanding is that we're going to raise so much revenue in the U.S. from tariffs that the federal government should be able to basically spend money on whatever it wants with no real drawbacks or trade-offs. So I think we're going to be entering a new golden age of science pretty much any moment here, from what I can tell. I may have misunderstood something, but
I'm not an economist by any means. Stonks is right. Invest, buy in the meme stocks. All right, Actual Education wants to know, what do you think about the Texas Super Collider, or the would-be Texas Super Collider?
I mean, so that book that I referenced way at the beginning of the stream, for those that were with us at that point, The God Particle, this Leon Lederman was basically writing a popular science case for the superconducting super collider. And knowing what we know now, the superconducting super collider would definitely have had sufficient energy to discover the Higgs boson, and might have done so somewhat earlier than we ended up discovering it in the end. But the one of the reasons that the SSC was canceled was that it really was, I think, falling into some technical trouble. I don't want to get too technical on the stream, because we would have to discuss a lot about how particle accelerators work in order for it to really make sense. But to some extent, the like aperture, the size of the beam in the accelerator determines to a large extent its cost. Like, you can imagine that if you have to build an accelerator to contain a beam which is like twice as large, then like basically all the magnets and everything you have to build also have to be twice as large. And in many cases, these things are expensive to fabricate. They may use rare like superconducting materials in the magnets, et cetera, et cetera. So I think there were some, it was cutting edge research at the time, but there were some kind of, I think, unlucky or maybe even unwise choices made in the sort of overall development of that machine that made it a riper target for cancellation than it might otherwise have been. So it's entirely possible that in the event that we actually built the superconducting super collider, that the LHC on more or less its like same current schedule, it might have been the LHC might also have been accelerated, right, in order to accelerated in the schedule sense, not just the like particle physics sense, might have still ended up being a credible competitor to the SSC. I'm not sure how much different physics would really look now if we had actually done the SSC, because the LHC was going to happen either way. It would have been significantly lower energy, but significantly higher luminosity. So in terms of the actual production rate of like Higgs bosons, for example, the difference might not have actually been that large. And I think a lot depends on the specific technical problems that they would have ended up encountering on that project. Oh, the corrupt blade.
What is that?
Who is he? This guy. I guess this is the guy I've been looking for. So you have like these different kind of like mafias of people that inhabit different regions of the world, and you're kind of like tracking them down and assassinating them one by one. So I got these guys a while ago, and I guess now I'm finding these last 3 guys that managed to escape me before. One of them just happens to be standing at the base of this tower. So yeah, I don't know. It's an interesting alternate history of what particle physics would have looked like in a world with the SSC. I think it would have definitely been good for American particle physics in particular to have a cutting energy machine on American soil. I think would have been a great boon to the US particle physics community. We would probably be bigger and more technologically advanced by now if we had done it. But in terms of like how would our understanding of physics be different? I'm not sure that it would really be that different. Again, knowing what we know now. Of course, if the new physics had turned out to be somewhat heavier, then, the Higgs is not particularly heavy. It's 125 GeV, so it's even lighter than particles that were discovered earlier. The top quark was discovered at the Tevatron, a previous collider in the US, that's 175 GeV, so significantly heavier. There's other reasons why some particles are easier to detect than others, but in a world where new physics was multiple TeV, then the superconducting supercollider would have had a much bigger advantage because of its higher center of mass energy. So it really depends, like, what is the alternate history scenario exactly.
Wow, and you don't know that going in. That's
you're designing for a range of possibilities.
Wow.
Even the Higgs mass, I mean, the mass that we found was one of the more likely outcomes, but there's not any formal reason why it has to be that particular mass and not some other one. So it's totally possible that, I think the standard model would still be self-consistent if there was a Higgs of like 1.5 TeV or something. That's near the upper end of what I think like theoretically was favored. And then the SSC, I think, would have been the right machine to build. But you can't know that until you do it. And once you know, there's not much incentive to build like another. They're so expensive and they take so many decades to build that you wouldn't like go back and revisit the same energy scale with like a slightly different machine, right? You just use the one. You have to take a stab in the dark, essentially, and then you try to motivate it as well as possible, of course. But I don't think there's any way to... It's hard.
Yeah.
Hindsight is 20/20.
So actual education, very cool. Appreciate the insight. I went to UT for undergrad, so it was a legend in my department. Yeah, the what would have been. I mean, locally that would have changed science for. I guess you don't have to be there to do a lot of
Waxahachie,
this.
Texas would be a very different place right now if the SSC had been running for the last several decades.
Lori, sorry I'm late. Tornadoes touching down here distracted me. That's unfortunate, Lori. Hopefully you're safe and having a good time. What's the drink of choice tonight? Let's put up the drink. So Ted brought over this one. Stone Pilsner is what we're drinking tonight.
I could use another one, actually, if we have them
let's
around
do
here.
it. You got...
This is a very crisp Pilsner. I think the last beer that I brought was also from California.
What did you bring last time? I couldn't remember.
Sierra Nevada Pale Ale.
I've had Sierra Nevada several times, but never Stone Pilsner. Where's this one from?
They're from San Diego, right?
Any particular choice
Escondido.
for this one? Any?
They have it at this gas station near my house that has a great beer selection.
That's amazing. Actual education. We have the best IPAs here over on the West Coast.
Yeah, no argument from me.
Y'all do have heady topper, though. Man, Misadventures wants to know, is China planning to make a large collider? That's true. China hasn't really dove into the big science, big funding endeavors.
Yeah, it's coming, I think. I mean, Juno, I think, is the name of their big neutrino experiment, a reactor neutrino experiment, which is kind of a follow-on to a big reactor neutrino experiment in China that was also successful, this Daya Bay experiment. Physics departments in China have been growing very quickly over the last few decades. They tend to be, I think, more focused on a lot of things which are a little bit more applied in many cases, which I think kind of fits like the Chinese ethos of development in a way. A sort of a practical a sort of a practical approach to like trying to drive innovations that will like have a shorter route to benefiting industry or something like that. But I think, it's a big country. There's a lot of smart people and there's a lot of money available there. And I think, there have been discussions of a future collider in China. Relations between China and not only the US, but some of its other neighbors like Japan are not the best. And even if China has a lot of money to throw at the problem, it's not really something I think that one country can do on its own. There's certainly not enough expertise and like high energy physics infrastructure there now to do it by themselves. And I think there's like, especially with all these export controls on electronics and stuff, I think the road to like actually pulling that off has gotten significantly harder in the last few years. So I don't know what the powers that be in China are like thinking about that idea. There's like some really interesting problems connected to like doing basic research in like a totalitarian society. Like research enterprises in China often are like having someone that like reports to the like Chinese Communist Party, right? There's like commissars or whatever of like universities and stuff there. It'd be a real culture shock, I think, for people coming from Europe or the US. So I don't know. It would be an interesting adventure. For a long time, it seemed quite likely that there was going to be a future collider built in Japan. This like linear collider idea that the Japanese have invested a lot of R&D and stuff over the years. That also seems to be somewhat on hold. For a while, I was like assuming that I would end up doing research in Japan after a certain point. Now I'm not as certain that that's what's going to happen. But because of the global nature, because of the decades-long timescales, like planning is a real big deal in our field, and we try to. We have like in the US this thing called the snowmass process. There's an equivalent thing called European strategy process, which are basically attempts to get all the physicists like together in one room talking to each other about what future facilities should look like, because we can probably only afford one if that. But it's also, there's something of like a first mover problem, right? Of like, in the end, you do have to pick a site, and it has to be like somewhere and not somewhere else. So, who's going to be willing to kind of take the leap of faith to make the commitment to like rally other people around it? It just seems like a hard problem, like politically. I think like Japan was kind of waiting maybe for stronger indications of interest from other countries, and the landscape is always shifting too, right? Again, I think at a certain point we thought there might be a lot of new particles like flying out of the LHC, and then the case to build one of these like future lepton colliders would be super strong. Now that hasn't happened, it's a little less clear exactly what the physics program would be. And that's part of the reason that these ideas for like something more, sort of a bigger technological leap, like this muon collider, have gained some currency. There's a lot of people, especially young people in the US right now, who are really interested in this muon collider idea, because it would be a way for the US to kind of jump the queue of these big projects and like retrieve a sense of technological leadership that we've kind of lacked for a while now in the field. But it's also risky, and like funding agencies hate risk. The chance of like pouring billions of dollars into something that then is like a technical failure, that's like a worst case scenario for like the funding agencies, right? They might not survive their like questions that would be asked of them by their political oversight if that were to happen.
When you say technical failure, it's not just that it wouldn't work or it wouldn't give the results we're expecting. Well, what does technical failure look like?
I think in the case of a muon collider, it's yet to be demonstrated that it would actually work.
Wow.
I don't know that there's necessarily a showstopper, but there's lots of R&D that would have to be done. And because we're always in a limited, funding limited situation, long-term R&D is something that's always looks easy to cut, because it's like, well, we have these existing experiments that we need to ensure. Yeah.
Cool. What is that? Oh, that's defeating the boss? Did you get him?
Yeah, I hope nobody ever calls me the corrupt blade. That seems like a not nice thing to be known as.
Turns out that's what your students call you behind your back.
Oh,
Go to your Rate My Professor right now.
oh yeah, don't go to my Rate My Professor. I think the people on that webpage have an axe to grind sometimes.
Oh. It's like the students either really love you or really hate you, and there's no in between on that webpage. Oh, man. So Misadventures had a follow-up. They're building big radio telescopes, so I was curious if they had been doing something similar in particle physics.
Similar how?
Just in terms of pursuing big science. But radio telescopes are much easier, as far as I understand.
I guess it depends how big you're making them. But radio telescopes, I think, are like more an example where you have one kind of like unit that then you can repeat, right? So you have like a radio telescope, and then you can make like an array of like N radio telescopes. But it's not like you have to. It's not like you have to invent, compared to a telescope, which is like, there might be very difficult technical requirements in the sense of like the resolution of the telescope and the quality of the optics and stuff that may be challenging to achieve. The different types of technologies that you need for like an accelerator and detectors, and that they all have to work together and be available at the same time, I don't think is a really close analog in astrophysics. You do have these spacecraft that will have multiple different types of instruments, like a spacecraft that will have different instruments that look at different parts of the electromagnetic spectrum or whatever. And then you're kind of getting into the territory where it's analogous to a particle physics experiment. But, just there's all kinds of problems inherent in like our whole experiment has to work as like one organism. We talked earlier about this idea of triggering, right? So like, because we can't afford the bandwidth or the disk space to record all of the data, you have to build into the experiment itself its own intelligence to be able to evaluate like what kind of event it's seeing and make a decision 40 million times a second whether to write out the event or not. So there's absolutely no chance for like a human to like get involved and like check the work. You can use simulations and you can look at the output and try to confirm that things are working the way that you are, but in the end you have to trust the experiment to like decide for itself which events to look at and which not. And I know maybe there's some things, LSST, whatever, where you're kind of approaching this sort of problem in astrophysics, but I think it's like a little bit different. Generally in astrophysics, the question is like, who gets the time on the telescope to decide where to point at? Trigger bandwidth is like kind of like that in particle physics, but only in an abstract way. It's a different sort of challenge.
So Misadventures had a follow-up on that. Their fast telescope is twice as big as Arecibo, for reference, or it will be when it's finished. Arecibo, that's in Puerto Rico? Where was that?
Yeah, it's like broken now.
Yeah, I think it's decommissioned, or they decided not to renew it. Actual Education said they do fusion, so China is working on fusion, but again, the scale of that is very different. It was RIP. Ooh, pour one out for Arecibo. Cheers. Mine Hire, thank you for the follow. Thank you for joining us on Ask a Scientist Gaming, mediocre gameplay, expert science. If you have questions for Ted, he's happy to answer them. It's 10:22, so we have about, I don't know, how long do you think it's going to take you to beat NARC? Fastest time of any of our guests was 16 minutes. The slowest time is 38 minutes. Let me look up your previous time.
I'm guessing I'm going to be somewhere between maybe at 10:30 we switch over.
I don't know. You're a gamer. Let's see what your previous time was.
You keep us all in a spreadsheet.
Oh, I do. I know exactly where you're sitting on the spectrum of.
How dare you just reduce me to a single number? I'm a human.
Yeah, exactly.
Dreams and hopes.
Well, where are you? So last time you were 22 minutes and 22 seconds. So that's a pretty solid time. I'm going to say you're sub 20. It's going to come down to...
I remember spending a lot of time walking in the level that I was supposed to be riding a car. So I feel like if I can keep that car a little bit longer, it will help my time enormously.
You're exactly right. And you remember the boss fight, right? Jump rocket to the head. I'm going to put you sub 20 minutes this time, but maybe we'll do a prediction for that.
I usually flourish when high expectations are placed on me, so I appreciate
awesome.
your confidence.
Let's do the stress. You're going to play this for 17 more minutes, and then we're going to NARC. But anyway, Lori has redeemed request a factoid. Fun factoid, Ted was the one that pointed out our use of factoid is incorrect. The actual definition of factoid is something that is fact-like. And in retrospect, I should know that because humanoid, an oid, it's a Latin root for similar. But nonetheless, we kept the term factoid. So Ted, do you have a fact you would like to drop on the audience?
Maybe I'll repurpose one of the...
Just a side note on that. I've never forgotten that you pointed that out, but one of my favorite equivalents of that was when Neil deGrasse Tyson went on Daily Show and said the Earth was spinning backwards in the introductory video. But anyway, sorry, go ahead. What's your fact?
I was going to give a factoid. So I think a lot of people in physics, whatever, have this impression that, like in the past, things happened much faster. There was like so much less bureaucracy, and people were able to just like write letters to journals like very quickly. And certainly to some extent that's true. But I learned a factoid the other day that I thought might be interesting to share with you, which is about the famous Rutherford experiment. So this is where Ernest Rutherford in Manchester was using a radioactive source, and then he would pound a gold foil like extremely thin, or I guess you roll out a gold foil extremely thin. So it's just a few atoms thick. And then he observed that sometimes these like alpha particles, instead of just penetrating the barrier, would be thrown back in the other direction, which was totally inconsistent with the ideas at the time. There was this like plum pudding model of the atom, which thought that the positive charge was like diffuse and the electrons were somehow embedded in this thing. And so the fact that you had these super high recoil events indicated that wasn't the case, and that the positive charge must be concentrated. It's at the beginning of nuclear physics, basically, that there's a positive charge concentrated at the center of the atom, and that's what these things were reflecting off of. Well, I learned that he spent 2 years reanalyzing the data from this experiment, because like he himself was not confident in it. So like we complain in our experiment CMS, for example, that a lot of times it takes like years for publications to reach the stage of being public, and that it would be better for like young people in the field, etc., if we could really speed this up. And so I just thought it was interesting to learn that it's not necessarily the case that just because someone was working 100 years ago that they could just like lively like publish their data very quickly, and that this is like a modern problem of things being so bureaucratic. So like the fact that it took Rutherford 2 years to actually get this earth-shattering discovery into a publication really changed my perspective a little bit on like the time that it takes to publish results, and maybe what's reasonable to expect or not. So I had naively assumed that he probably wrote a letter to the journal like the next day about this discovery, but not the case at all.
Well, I mean, he spent a lot of time rationalizing, because the original experiment, he just wanted to know how much it absorbed, right? Like how the transmission coefficient for gold. And then he's like, well, that's weird. This adventure's looked up fast. It's 4.5 football fields wide.
Okay.
The radio telescope. Holy crap.
That is big.
Yeah.
And then it's covered in some kind of like, it's a radio telescope, so you don't actually need like a solid sheet of metal, right? It's like a kind of a metal lattice
like a
that
field.
reflects the radio waves, right?
Strawberry Bunny, thank you. Strawberry Bunny, thank you for the follow. Thank you for joining us, Ask a Scientist Gaming. We're playing some Assassin's Creed Shadows while we are, talking about some particle accelerators, high energy particle physics, astrophysics. We've been through all the physics space, right? I don't think we've missed out. I guess condensed matter has been avoided, except talking about detectors.
We talked about radiation damage to materials. That's so cool. Somewhat related to condensed matter.
Like as a chemist, I'm thinking about this particle soup that you have to deal with, right? You have like, beta particles and gamma particles and neutrinos, and the sequence which that hits and when it hits will change the reaction and what the products of that reaction are. And that is mind-blowing to me.
I mean,
Not predictable.
For the project that I'm working on right now, actually a lot of it comes as neutron radiation, and normally when you think about radiation, you think of like fast moving particles traveling in a straight line, but neutron radiation is a really interesting and difficult problem to deal with, because neutrons are really better thought of as like a gas than as like rays coming off of a source. So like we have, for example, like cracks and pathways in our detector to allow like optical fibers and power cables and stuff to come in and out of the detector, because everybody needs their own services, their own powering, their own bias voltages, whatever, to be delivered. And neutrons will actually like go around corners, like so they can follow because they're kind of bouncing around slowly, and a neutron lives like 10 minutes or something, so it can travel quite a long distance even at low speed. So neutrons, unlike most forms of radiation, they will like follow the contours. If you have like a pipe, they can actually move through the pipe kind of like a gas, which is not usually how people think about radiation. I mean, I guess if you're worried about like radon in your house, that's maybe more of like an analogous kind of situation where you actually need to stop the radon particles from like traveling through the air. But yeah, so shielding from neutron radiation is like a whole different ball of wax. And it turns out one of the best ways to do it is to actually just put hydrogen-containing materials around, because a hydrogen nucleus has about the same mass as a neutron. So when there's a scatter, it's like a bowling ball hitting another bowling ball. A large fraction of its energy will be given up to that proton, which is charged and therefore will range out in the material very quickly, as opposed to a neutron, which is neutral and would just like float through. So literally like wrapping things in plastic can be a good way to shield from neutron radiation.
That's awesome. All right, we should do one more prediction before we start NARC. Which one do you want to do, quarks or antimatter?
Yeah, let's do like a back of the envelope estimate, a kind of like problem. So maybe people who have some quantitative skills can take a moment to think about this. How many quarks are there in a banana?
All right, ladies and gentlemen, we're going to give you 2 minutes to do this. Don't do the calculation, at least with the calculator, ChatGPT, or Google. Just with what you have in your mind, what you understand about the number of quarks and, I don't know, mass of a banana. Can you translate that to number of quarks in a banana? This is a fun, like, Gen Chem 1 question, actually.
Yep.
Well, Gen Chem 1 plus some physics. Yeah,
a little bit.
Know how many quarks are in a proton neutron.
Yeah. What's a factor of 3 amongst friends?
Spoilers. Give away the answer. But yeah, this is a fun calculation. So you guys put your predictions in there now. Click the predict button. Is it greater than 10 to the 24th? Less than 10 to the 24th? That's 10 with 20 or 1 with 24 zeros behind it. Yeah. No one tell RFK. Oh no. Getting too political. I got the warning. I served on an NSF panel today, and I learned that during my duties as an NSF panel member, I cannot make any political statements. But as of 6:30,
seems like a fair rule.
In general. Old man Felonius, welcome back. Banana quarks. It's quarks all the way down. Quarks are bananas. Oh man, put your predictions in there now. Yeah, how many quarks are in a banana? Curious how many people know this versus how many people guess. Man, this is the kind of question I like on like Gen Chem exams. I don't like, calculate the exact answer, because if you get something wrong, but if you're like 3 orders of magnitude wrong, then you don't understand at all. Like you have no concept of what these scales are. But yeah, we're going to see for this one. So yeah, put your predictions in there right now. How many quarks are in a banana? Greater than 10 to the 24th, less than 10 to the 24th. The answer is not exactly 10 to the 24th, is what we're going to, spoilers on that. Depends on the size of the banana. Is that... If you have a banana as large as the moon.
I would say bananas fall within, let's say, a factor of 2 in size, generally. All the bananas I've seen anyways.
Error bars on banana size. All right, Ted, what is the answer?
All right, so I'm going to say a banana is about 100 grams. I looked it up. They said bananas, maybe they max out at 150 grams. Let's say 100 grams just to keep it the math easy. Mm-hmm. And then if we were calculating the number of atoms in a banana, it would actually be a somewhat harder problem, because then we would have to know what kinds of atoms they are. But actually, in this case, we don't, because the number of quarks in a proton or neutron is the same. It's 3.
Oh, yeah. Okay.
And so
doesn't matter.
The mass of the banana is mostly made up of all the nuclei in there. The electrons contribute almost nothing.
Yep.
And so whatever atoms it's made up of, that's going to cancel out in our calculation. So if we have 100 grams, that means that there's 100 times Avogadro's number of protons and neutrons in there, right? So let's just imagine the banana is totally made of hydrogen, which isn't accurate, but it doesn't matter. So 100 grams of hydrogen would have 100 times Avogadro's number of protons inside, and you can pick whatever element you want, and that just cancels out in the calculation.
That's
so
fun.
100, that's 10 to the 2. Avogadro's number we can call 10 to the 24, 6 times 10 to the 23rd. And then there's a factor 3 in there because there's 3 quarks in each proton and neutron. So let's say 10 to the 24 times 100, 10 to the 26. So there's something like 10 to the 26 or 10 to the 27 quarks in a banana.
That is
I find kind of an amusing number.
That's a fun one. I mean, the key to this one is you need to know Avogadro's number. If you know 10 to the 23rd, I think you could guess, basically, right? It's going to be big, greater than 10 to the 24th. I guess if you know a banana is 100 grams, that answers the question automatically without the scale of 3. But yeah, congratulations, those of you that got the payout. Everyone guessed 10 to the 20, greater than 10 to the 24th. So
one thing I didn't appreciate before I was teaching the class that I'm teaching now is actually Avogadro's number used to be one of the limiting factors of the precision to which we knew Planck's constant, because the way that people measured Planck's constant back 100 years ago was using X-ray diffraction of sodium chloride crystals. And so you have to know what is the interatomic spacing of the lattice in order to figure out where the diffraction fringes at what angle they should be. And you know the density of salt, but you need to know Avogadro's number to convert that into an interatomic spacing, to know how many atoms per unit length are in the material. So for a while, this was one of the... Planck's constant was a derived constant from Avogadro's number. Not true anymore, but...
That's pretty cool.
That's kind of a funny thing.
All right, are you ready for your journey in NARC?
I am.
I'm going to get the live split. Where are you, live split? Got to get the... There it is. All right, we have the clock in the corner. All right, we're going to go to our talking heads for a bit before we change monitors. No, I do not want to update. Live split works perfectly fine the way it does. Ken talking about orders of magnitude, Fermi would be proud. I talk about orders of magnitude a lot, especially with time resolved spectroscopy, because the difference between pico and femtosecond is pretty large. All right, what is this?
Using like femtosecond laser pulses?
Yeah, we do time resolved spectroscopy, so we do everything between femtoseconds and seconds. So we cover, 13 orders of magnitude of time. So yeah, students
think about distributing a picosecond clock through an experiment that's 15 meters in diameter, right? It's a non-trivial challenge.
What's cool about femtosecond measurements is the way you control the time between a pump and a probe is by distance, right? Because a foot per nanosecond? So you can actually use distance.
3 nanoseconds per meter. Yeah, that's what I always think of for physics. Yep.
Yeah, that's pretty fun. All right, so before you press start on this, since you were on here last, have the original Nintendo cartridge in a plastic case. And so there it is, ladies and gentlemen. NARC. It was about $45. So
probably what it cost in 1984 or whatever.
It's not a high demand game. Nerds, absolutely right. If you guys are nerds, you're in the right place. But we're playing NARC. This is how we close every single one of our streams. If you're new to the stream, this is the bargain bin game that I make every single guest play. And we time how fast they beat this game. They have infinite lives, infinite rockets, infinite bullets. But we also have the original cartridge, which gives us the back. So you're going to learn the lore. I don't think you learned the lore last time you were on it 3 years ago. So NARC, no one had the guts until now. You are Max Force. Your mission, bust Mr. Big and destroy his dreaded criminal empire. Seize all contraband, stolen money, illegal weapons, use rocket bombs, high-powered machine guns, apprehend all suspects, protect the innocent, punish the guilty, stop at nothing. Should we put a prediction on whether you're going to break 20 minutes?
Oof. Why not?
You want the pressure, right?
If only the fentanyl crisis was as easy as finding a guy with like a robotic spider body in a warehouse to just shoot with a rocket launcher.
All right, ladies and gentlemen, we're going to give you 30 seconds to predict Ted's time. Note his previous time was 22 minutes. Is 20 minutes a fair over-under?
I mean, that would represent a 10% improvement.
So you think
seems achievable, right?
Is it too easy, though? Should we go 19 minutes?
Ooh. Well, you would know better than I what's required to shave minutes off this game.
It's really going to come down to what you do against Mr. Big, but we're going to start the prediction right now. You guys have 30 seconds. What's Ted's time in NARC going to be? Greater than 20 minutes or less than 20 minutes? Oh, here's the other one I picked up at the same time.
Oh, famous shovelware disaster.
ET for the Atari.
Do you have an Atari?
I don't have an Atari. We can play ET on the emulators. I don't actually have an original Atari.
Maybe for episode 200.
Yeah, exactly. We're at the party. We just set up ET. Everyone gets to play. All right. Oh, man. So only a few people bet, but they're confident you're going to do less than 20 minutes. All right, Ted, Are you ready for this? Go ahead and press start.
Ready as I'm going to
walk you through. But you guys can distract Ted by making him take a drink. Also, you can ask him all sorts of science questions because he's going to try to focus on NARC and beating this game as fast as he can and beat his colleagues and his wife. So we're going to see how this unfolds. You guys have to tell me how the volume is. I think it might be a little low, but maybe that's a good thing. But yeah, the goal in NARC is you're trying to beat the game as fast as you can. There's no real advantage in killing other guys, especially when you have infinite lives. But yeah, tap A is rockets, press A is bullets, tap B is jump, hold B is squat, and yeah, try to go as fast as you can. And so
there is a time penalty to getting shot. So
yeah,
I would say
every 7 times you get shot, you lose a second.
These stupid dogs, man. I hate the dogs.
And if you remember correctly, the Mr. Big at the end, you have to do a jump rocket, so that's something you could practice as playing as well. And the Misadventure is trying to mess with you as at request to redeem a factoid. You have one you want to... let's use your other prediction we didn't. You can use this as your... yeah, right there. The antimatter to power a car.
Right. So another sort of order of magnitude estimation question, which is how much antimatter it would take to power a car for a year. Of course, it depends a little bit on like where you're driving, et cetera, et cetera. But I guess we're not taking a prediction.
No, we got the prediction set. So
the important thing here is that there's a tremendous amount of energy locked up in the rest mass of materials, right? So even in a nuclear reactor where you're turning some of that energy, some of that mass directly into energy, it's actually a really tiny fraction of the starting mass that gets converted like in a nuclear reactor. We're talking about a fission reactor here, which is like a fraction of a percent of that rest mass, which is disappears in that interaction. Whereas in antimatter annihilation, all of the mass is converted into energy. And as we know from Einstein's famous expression, E equals mc squared.
Sorry to interrupt, but in this region, you're going to want to shoot the guys wearing black with bullets, and one is going to drop a blue card. So yeah, hold the shoot button. Yep,
there we go.
And you're going to want to shoot them at close range in this region, because that's the way Nintendo works. I don't know, so go back this way.
I just got to keep farming this region.
So it's random number generated. It's like a 1 in 8 chance one of them will drop a blue card.
So that's a big thing in your
the speed run.
Speed run, right?
Yep, this is one of the kill points. Yep. It's gonna make or break the predict. No. Usual time on this is so go back. It has to be in this like
in front of these
door.
Tanks. Oh.
Yeah. So shoot
see the black.
Yeah.
There he is.
So they can only have like 3 sprites on there.
There you go.
Blue card. All right.
What?
Hitboxes.
No.
There we go.
This game's like glitching out. I guess the CRT helps to like
you make it look not terrible. Yes.
Steer all that out. So it turns out to be a super tiny amount of antimatter. Just 1 milligram, not even of antimatter, would be more than enough energy to power the average American's car for a whole year. And so that's why like the idea of the Starship Enterprise, right, to like to carry antimatter as your like fuel source would actually be a really good idea for a spacecraft, because most of what a spacecraft is doing is carrying fuel to move around the fuel that it's carrying. So if you can get rid of most of that mass, you can actually build a much better...
So here's the car, jump in. You're going to stay on the bottom, but you're going to run into a wall eventually. Yeah, you don't really have a choice there. Lori cheers. She requested take a drink because we drink and drive on NARC. So Ted, thank you again for joining me, especially on short-term notice for the 100th stream of Ask a Scientist Gaming. So yeah, this is the Saunter the Bridge level. And I mean, the hard part about antimatter is you have to contain it, right? So how do you think Star Trek did it?
Strong magnetic fields, right?
Just suspended.
That's what's going on in the warp core, I think.
Yeah. I don't know. I like press jump. I like
I should be practicing my jump rockets, right? So I need to press this and then...
I like sci-fi that doesn't try overly hard to rationalize. It's just like, if you accept this one axiom, you're fine, right? If you accept that Star Trek and the Enterprise can, you know, contain it, that's it.
Yeah, I mean, is it easier to accept that people would invent a way of containing antimatter, or that, like, there will be a future without, like, poverty and like political strife? I'm not so sure which is less realistic.
Oh. Man, so we haven't gotten to the two juicy questions I like to ask, but it's been 3 years since you've been on the stream. Any movies or TV shows you've seen, maybe a three-body problem, something that was physicsy related that made you cringe or made you happy? Anything?
Well, you know, I just watched the very first thing of the three-body problem series, where he's getting like pilloried in the Cultural Revolution for being like a believer in Einstein or whatever.
Yeah,
it really happened to people.
Mm-hmm. Which is insane. All right, so get in the car. You're gonna tap. There you go. So you're gonna stay on the bottom, go up, a little higher, and that'll get you some distance. Then keep going. Yeah, it's short of, so after the barrels, you have 3 seconds of driving, and then you have to go down, but short of memorizing.
Yeah, this is the sort of thing that I was hoping to practice for last time.
Here's the thing, I'm going to send you the tutorial.
I'll do it, man.
No, if you get, let's look at the NARC speed run.
I'll do it. I think I have the tools to, like, record a run, right? If you have an NES emulator, you can, like...
And even this OBS software can readily do it. But yeah, it's not... NARC saunter. All right, so fastest time is 9 minutes and 4 seconds. My fastest time is 9 minutes and 7 seconds. Third place is 9 minutes and 36 seconds. If you get a sub 10 minute, you are top 5 in this game. So you could easily be top 5 with the Ken Hansen YouTube tutorial. That goes for anyone that's watching right now.
So what do I search on YouTube? Just like
I'll send you a link. If you just NARC speedrun tutorial, there is one answer, and it's going to be my.
Oh, there's not going to be a whole universe of NARC speedrunning channels.
Not a competitive strategies.
Oh, there's a clown.
But my brother did do a tool assisted speedrun, which is kind of fun. I don't remember the time. It's like 8 minutes and 53 seconds or something like that. But he optimized a whole lot of this game.
Optimized just meaning practiced really a lot?
So the tool assisted speedrun, you basically control every input per frame. So
I see.
You can make essentially the perfect run. So go through that door right there. You're going to go to the right, and you'll pick up a white card. And then when going out this door, you don't want to press up too much, or it'll put you back in this room. So, yep, that card right there. Press up, but not too much. Go left. There you go.
I feel like I must be ahead of my split from last time.
I think so. I think you're flying. Abadus, welcome back. Howdy, y'all. Thank you for joining us. Ted Kolberg's talking astrophysics, but also, not astrophysics, high energy particle physics. I apologize. But we also talked astrophysics, so there we go. But yeah, if you have questions about Large Hadron Collider, CMS detector, smashing protons, Higgs bosons, whatever it might be, feel free to ask them while Ted tries to go as fast as possible in NARC. In fact, we have a prediction pending this. You're going to go left on this level. And what you have to do is these green Rambo looking guys, you have to shoot them with bullets at reasonably close range, and one of them will drop a green card. So go, yep, so keep going left. Yeah, keep going. You get closer to the door. Oh, there you go. Speed strat. Ted's on a roll, ladies and gentlemen. The pressure. You're feeling
I'm in the zone. I don't feel anything. I just, like, my brain is totally out of the loop. My fingers are doing all the work.
This is unconscious. He's feeling the flow, ladies and gentlemen.
Yeah,
you can break that flow about talking about particle physics, or, you know, just let him play a little bit. I'm just waiting for the LHC to open a portal to another world so I can jump in and get off this one.
Well, careful what you wish for. Who knows what could be going on there.
I mean, you could use the Large Hadron Collider if you just like put your head in there.
Or you go to the
It'll
world
take you
where like
somewhere.
everything is great. There's like all these like enlightened ideas and stuff, but like the food has the wrong like chirality, so you just
You
die.
starve. Or there's no NARC in that universe. I think of the tragedies. Can they hurry up with black holes too? You got the audience demanding these changes.
I mean, this is something that we again thought there was like a chance that we might actually produce and observe them at the LHC. I think it's largely excluded now, but you never know.
Yeah, I read a sci-fi book where that was the central premise. They had started making mini black holes, and there was a cult developed around it. Kind of fun.
Okay.
One thing you might want to practice here is the jump rocket.
Yeah,
So
that's what I was
tap
trying to
B.
do. So I tap B and then tap A while I'm in the air.
Yep. So basically when you're at peak, yep, there you go. So you're a little lower will be a rocket shot. But you're pressing it a little too hard, but you have this card, so you can go there right away. That does sound fun. The crippler, back to the non-ergonomic
I tell
NES
you,
controller.
the PlayStation controller is just a lot better.
Oh my god, no, this controller was not designed with any spaghettification cults. That
That's
is
the
amazing.
other-
I've never heard that phrase.
Cool thing about the PlayStation 5, right? This like high definition rumble or whatever. Like in that Assassin's Creed game, when it's raining, you feel the little like rain
Oh,
patter
that's
on your
fun.
hands while you're playing.
That's such a
Kind
nice
of
touch.
interesting.
So yeah, if you're not jumping, maybe tap it lighter. Yeah, there you go. Oh, it's going to be a little later on the rocket, but that's the idea.
Because I need to fall, right? He's not that tall.
His height is a little bit shorter. Your pace is excellent right now. There are literally imaginary internet points at stake here, ladies and gentlemen. And pride. Let's not. The fastest time anyone has beaten this is 16 minutes and 18 seconds. All right, so this guy you're going to shoot with a rocket. So you don't have to jump on him, just normal rockets. So just unload rockets. Internet honor. Sorry, I thought I read internet horror.
Some of those too.
Yeah. There you go. That's one. Inchworming. There you go.
I find
You
that
forgot about that.
Now I got to kill these guys to get the card.
If you kill them, he'll come back. So kill the guys on the screen, and then wheelchair guy will come back. And now you got to hit him again with a rocket. So just stand and shoot. A little lighter on the tap. There you go. So kill guys on the screen. He will come back. Oh, you arrested one accidentally. So yeah, if you see his arm come out or he shoots a bullet, you pressed it a little too hard.
Okay. It's tricky.
Yeah.
There's a lot of touch to it.
Oh, did we get the no budget, no morals experiment answer? No, we didn't. No unlimited budget, no moral qualms. What experiment would you do?
I mean, I feel like this is a more interesting question to people that do like biological research or something, right? I mean, what?
Yours
I
would
don't
be.
think it's that scientifically interesting to like subject a human being to the LHC. You know, this like Bugorsky incident, this guy in the Soviet Union that put his head in a particle
Oh
accelerator by
yeah.
accident.
Yep.
So I guess it'd be kind of interesting to try that.
No, Ted's answer is not build a faster or larger particle accelerator. It's put a person
Put a
in
guy
it.
in there. I mean, what else? What else can I do that's immoral? I don't know.
I mean,
I always thought it would be interesting
No,
to
the
see-
question doesn't say you have to be immoral. It just says no moral qualms.
You know, there's all this like fraud and like experiments that don't replicate in like other fields. I always thought it would be kind of
yeah.
a fun experiment to try to. I mean, if you didn't care about your reputation, to like see if you could fool people. I just wonder like how far it would go.
Undergrads, cover your ears. Yeah, these are your professors here negotiating. So kill the guys on the screen. He'll come back quicker.
Burning time here.
Yeah. Yeah, the best bet is just unload rockets. Or like stay on the middle of the screen and just unload and hope it hits him. Because aiming for him is non-trivial. So maybe press the button a little lighter. It's like you don't have to press it down all the way. Ooh, ooh. That was close. But yeah, if you guys have any questions, we've got about 10 minutes left. Ted is happy to answer those questions while playing NARC, while winning the war on drugs and meeting Mr. Big. Talking about particle accelerators, putting a person in the beam. I mean, I'd be curious if you just put a hand in the beam, I mean, potentially cancer, but it would essentially burn a hole through you, right? Depending on how long you put it there. All right, that's 2. You need 1 more against him.
I swear the hardest part of this game is getting the rockets to come out reliably.
Yeah. Just touch it a little gentler. There you go. Yeah, it's one of those very few Nintendo games required you to like control your pressing, right? It was a zero sum, either it's on or off, and this one it's pressure based. All right, he's going to drop a gold card.
No more informing for you, buddy.
No, instead, he's turned into something much greater. But what would like the Muon Collider? What would that cost to make? If you had to throw a number out there.
Some billions of dollars.
So what did the LHC end up costing in its finality? So go to the top of the screen, jump, and rocket in the hat. So at the very top of the screen, it'll avoid the tongues. Yep. Yep. So go this way, get a little bit of distance, turn around. Yep. Ooh, that one was close. That was very close. A little gentler on the rocket. This boss.
Such a bizarre
yeah,
idea.
it's just like, who made the executive decision that this needed to be the bad guy? So a little gentler on the A. So that one you hit 7 frames and you needed 6. Turns out if the bullet doesn't form, it was 7, or the bullet doesn't, or rocket doesn't shoot, it was, yeah, exactly 7 frames. Yeah, the A button. It's be a little touchy. This B's working well. So, do you remember Game Genie? The like codes you put in? So my brother figured out codes to make this much easier.
Okay.
There's actually Game Genie codes where you can modify the hitbox or where you have to hit him. But we don't use those because we want you to suffer through shooting him in the hat, which seems like a dumb idea, but... Oh, that one was close. Just a little gentler on the A button. Oh, that one's very close. Mr. Big. But yeah, if you guys have last minute questions, also if you have suggestions as anyone we should raid, preferably science related, but also, I don't know, Assassin's Creed related, we don't care. We're gonna hang out tonight and bring our viewers to somebody else. If you guys have suggestions, but also get your last minute questions in as Ted battles Mr. Big and tries to win the war on drugs, because this is what the 1980s used to look like if you're not old enough to remember. Did you have to do DARE program? We all did.
Our DARE officer brought like a cool car that he had confiscated from a supposed drug dealer.
Oh, there it is. All right, rockets to the face. There you go. All right, so now you're going to walk away from him and get between these black lines and shoot bullets at him. So we'll go down, shoot bullets. There we go. 2 vertebrae, 3 vertebrae. Go the other way. You're going to do the same thing. We're getting close.
I'm trying to shoot him in the neck.
Yeah. So he'll come down and then, yeah, it's basically you move up and down while shooting him in the neck. Oh, that's good. Down a little bit. You'll get 2 more. That's it. Oh, it is not going to take him a minute to beat this next level. So go through this. Then we're on to civil forfeiture the level. Last minute suggestions on who we should raid. Keep going. You don't need any of this gold. Just get to the end.
Yeah, but what's the fun in being a narc if you don't get to confiscate the property?
Exactly. Civil forfeiture the level. 19 minutes and 22 seconds. You did it. Whoever said less than 20 minutes, congratulations. You get the payout. Ted came in less than 20 minutes. You did say cut off 10%. Mahoodles is on. Thank you. It's always a fun raid.
Contact your local DEA recruiter.
I mean, you did it. Backup career. Here we go. Still has his 22 like last time. You do 1922. That's
crushing DT's record.
I mean, after you see the tutorial, it's gonna. What's sad about it is the tutorial is mostly find a line and walk straight. By a hair, exactly. Only a little bit.
Physics is all about the power of simple ideas to cut through the nonsense of a seemingly complex situation. So I'm glad to hear that NARC is the same.
Oh man, I think you'd like speedrunning. I don't know if you've looked into the communities, but the elegance of figuring out the rules of a universe and completely exploiting them to do things fast. I mean, yeah.
Yeah, it sounds very scientific in a way.
Yeah, that's what I love about it. That's why I really enjoyed NARC speedrun. It's not a great game to speedrun, but it's kind of fun when you figure out some of the glitches.
At least it's unique, right?
Yeah, exactly. Not a lot of competitors. So here's the, I closed the NARC leaderboard, but there's only 13 people on it. So you could be top 5 in the world.
That's something.
Yeah, exactly. Exactly. We don't get a lot of opportunities to be the best. All right, everyone. Thank you for joining us for Ask a Scientist Gaming, mediocre gameplay, expert science. We delivered on both tonight. Plus, we won the war on drugs, and Ted killed a bunch of people in Assassin's Creed. Played some card games. Played a little bit of what was the space one? Slipways was the game. So yeah, been through a journey talking about a whole bunch of particle physics, but also talking about space physics and a little bit of condensed matter physics. So we were all over the board there. Ted, any parting words for the audience? Anything you want them to know? Any profound nuggets of wisdom you'd like to impart on the audience?
Don't do drugs.
Don't do drugs. Just say no. Oh, man. All right, Ted, thank you again for joining me. That's awesome. I short-term notice, I really appreciate it. We are closing out our 100 stream. Thank you all in the audience for joining us repeatedly every 2 weeks. It's a lot of fun. Speaking of which, 2 weeks from now, our next guest we'll have on April 16th, Ashwanth Francis, who's a biologist. He studies virology, in particular, virus host interactions and virus replication. I don't know what particular flavor of viruses he's interested in, but viruses nonetheless, so it'll be fun to talk about. We actually haven't had a virologist on stream, so we can ask questions about COVID and all sorts of other stuff. So virology is a fun area. I don't know if fun's the word, but so it goes. But anyway, thank you very much. Suggest you wear a mask for the interview. We'll be in full character. I appreciate that. All right. Thank you all for joining. Stick around. We're going to raid somebody. I think we had a few suggestions in there. Science, Mahoodles is on. Yeah, we'll take a look and we'll figure it out. But thank you again. 2 weeks again, we'll talk about virology. I don't know what Francis is going to be playing. Apparently, he's not a video gamer at all, so this could be interesting. It could be a rough night of gaming, but a fun night of talking about viruses. So thank you all for joining us. It's always a pleasure. Ted, thank you as well for joining us. And yeah, we'll see you guys in 2 weeks.